Number 1 says if y is the product of x plus 1, x minus 1, and x plus 5, then what is dy dx? So dy dx is asking for the derivative of y with respect to x. And finding this derivative is going to be a lot easier if we take this polynomial that's currently in factored form and multiply out all the factors and get it into standard form. When I do that, I will be able to use the power rule on each term individually and find this derivative pretty simply. So let's start by multiplying out all three of the factors here. The order in which you do this doesn't really matter, although I think just looking at these first two factors, it's going to be a little bit easier if we multiply x plus 1 times x minus 1 first because they are conjugates, meaning anything in the form of a plus b and a minus b are conjugates, and when you multiply those together, you get a difference of 2 squares. So you don't really need to know that. It doesn't make a huge difference which order you multiply these in, but I'm just going to go with those first two first. So first we'll go just out to the side here, x plus 1 times x minus 1. X times x is x squared. X times negative 1 is negative x. X times 1 is positive x. And then finally 1 times negative 1 is negative 1. So combining those two middle-like terms gives me x squared minus 1. And this is what I was referring to earlier when I said if you recognize you get an a plus b times a minus b, you're going to get those two middle terms to cancel out every time. And you get a difference of 2 squares, like x squared minus 1 here. So that's what this piece equals. So we can actually rewrite y at this point as x squared minus 1 times x plus 5. And now we can multiply those two factors together. So let's do that. So I'll just do it out to the side here. X squared minus 1 times x plus 5. Again, I'm going to use the distributive property to multiply each term in the first binomial by each term in the second binomial. X squared times x is x cubed. X squared times 5 is going to be 5x squared. Negative 1 times x, negative x. And negative 1 times 5 is negative 5. I don't have any like terms to combine there, so that's it. So now we can rewrite y as x cubed plus 5x squared minus x minus 5. Now, all we did was rewrite y. We haven't really gotten any closer to finding dy dx. That is the derivative of y with respect to x. It's the expression that describes the slope of y at any given point. Now, if you've got a polynomial, the easiest way to differentiate these kind of functions is with the power rule. I'm going to go ahead and just write that out down here, just in case you've forgotten. The power rule says that if you want to find the derivative of an expression in the form a times x to the n, you take that exponent up here and multiply it by the coefficient, and then decrease that exponent by 1. So it's actually a little bit easier in practice, I think, than trying to look at that rule and make sense of it. Let's go through all these terms, and I think you'll hopefully by the end you'll see the pattern there. So dy dx, let's start with x cubed. We're going to bring down the 3 as a coefficient, and then subtract 1 from the exponent. On the next term, we've got 5x squared. We're going to bring that exponent of 2 down with the coefficient and multiply it by 5. So 2 times 5 is 10, and then decrease the power by 1. So 2 minus 1 is 1. On the next term, we've got minus x. Now there is an implied negative 1 here. So even though there's also an implied exponent of 1 here, so if I bring down that 1, it's still negative 1 times 1. So my coefficient's still going to be negative 1, but then I've got to decrease the exponent by 1. 1 minus 1, 0, and x to the 0th power is just 1. So this term is just going to be minus 1. And then the slope of any constant is 0. If you imagine like a horizontal line, the slope is 0. Anytime you've got a constant here like negative 5, the derivative is just going to be 0. So there's going to be nothing left on this derivative. That's going to be your answer for number 1. Looks like the answer choice is C. Number 2 wants us to find the integral of root 9 minus x squared from negative 3 to 3. So as you should know, whenever you're finding a definite integral, what you're really looking for is the area bounded by that curve and the x-axis. So it's really important that you understand what this curve looks like. Otherwise, you're going to have a hard time with this problem. You might try to do maybe a u-substitution or something along those lines, but honestly, you really want to know what this graph looks like because it makes the problem a lot easier. So here it is. Basically, this is the top half of a circle. It's the graph of a semicircle. The graph of a semicircle is going to look like y equals the square root of a squared minus x squared, where a is the radius of the circle and it's centered at the origin. So once you realize this, you can start to visualize what this function is going to look like. Since the radius is 3 and it's centered at the origin, we can go out 3 spaces and draw the top half of that circle. Now, the reason why looking at this problem visually is so helpful is because you should know what the formula is for the area of a circle. The area of a circle is pi r squared. It's a pretty common formula, and I think it would be reasonable to expect you to know that. Now this is just a semicircle, so it's just half that. So area of a semicircle would be 1/2 pi r squared. And so essentially that's what we want. We want to find the area under this circle from negative 3 to 3, which just so happens to be the boundaries of that circle, so it works out really nicely. Here's negative 3, here's 3. So the integral from negative 3 to 3 of root 9 minus x squared dx is simply the area underneath that curve. So half times pi times the radius, which is 3 squared. 3 squared is 9, and half of 9 is, well, just 9/2. So we get 9 pi over 2, and our answer is D. Number 3 says, which of the following is an equation of the line tangent to the graph of f of x equals x cubed minus x at the point where x equals 2? So here we're trying to write a linear equation. That's an equation that when you graph it, looks like a line. And we're going to write it in point-slope form. So just as a little reminder of point-slope form, that's y minus y1 equals m times x minus x1, where m is the slope, and then the x1, y1 is the point. So to approach these tangent line problems, you need to find both the slope and the point. If you look at all the answer choices, they're all kind of set up in the same way. You see that they are set up in this point-slope form. And so let's start with how we're going to find the point, how we're going to find the slope. Well, we want the point and the slope at x equals 2. That's the x value of the point. So for my point, I have my x value, which is 2. And then to find the y value, I need to find f of 2. Basically, I need to substitute in 2 into the original equation. So if I substitute in 2 into f of x, that's going to give me 2 cubed minus 2. 2 cubed is 8. 8 minus 2 is 6. So f of 2 is 6. So now that we've got the point that we need, and you can see from all the answer choices, that doesn't really get us anywhere because all of them have 2, 6. But now let's talk about the slope. The slope is going to be the value of the derivative of f of x at x equals 2. In other words, f prime at 2. So we need to find the slope of f when x equals 2. They gave us the equation for f, x cubed minus x. So let's find f prime. In other words, let's find dy dx. F prime of x is, using the power rule, 3x squared minus 1. And so if I want f prime of 2, in other words, the slope of this line when x is 2, it's going to be 3 times 2 squared minus 1. So 2 squared is 4, times 3 is 12, minus 1 is 11. So the slope at x equals 2 is 11. Now I've got my point, and I've got my slope. So that's what I needed. Now I can go ahead and write my equation, which is going to be my final answer here. Y minus 6 equals 11 times x minus 2. The answer is D. Number 4 says the function f is given by 3x squared plus 1. What is the average value of f over the closed interval? Now, normally when we try to find the average of a set of data, we simply add up all the numbers in that set and then divide by how many there are. But in this case, we have infinitely many values. Just to give you a little visual of what's happening here, 3x squared plus 1 is a parabola with a y-intercept of 1. Looks something like this. I'm not going to put any more detail on that. I just want to give you a quick visual. And we're going to find the average value from 1 to 3. So if 1 is roughly here and 3 is somewhere over here, we want to take like all these points along the function, and it's sort of like we're adding them up and then dividing by how many there are. But there's a little bit of an issue with that because there are infinitely many points. We can't really divide by infinity, can we? So instead we're going to do a little calculus to calculate this average value. Now if I were to plug in 1 into this function, 3 times 1 plus 1 is going to be 4. Right? So this value right here is 4. And if I substitute in 3, 3 squared is 9. 9 times 3 is 27, plus 8 is 28. Now since our minimum value is 4 and our maximum value is 28, that means our average has got to be somewhere in between there. So as we find our value, if we get something like 35 or 1 or even something negative, then that definitely means we did something wrong. So let's go ahead and go over this whole idea of average value and how we compute this if we do have an infinite number of values that we're trying to find the average of. So to find the average value of a function, you're going to integrate on the interval you're interested in, f of x dx, and then divide by the difference of the two x values on the endpoints of the interval, b minus a. If we have a function 3x squared plus 1 as our f of x, and our intervals from 1 to 3, the integral from 1 to 3 of 3x squared plus 1 dx all over 3 minus 1. Now to take a definite integral, in other words, to evaluate this, we have to anti-differentiate the expression in here, and we'll use the anti-power rule to do that. And then we'll substitute in the endpoints here, 3 and 1, into that antiderivative and find the difference between them. So let's find the antiderivative of 3x squared plus 1. That's going to use what I'll call the anti-power rule, which is just pretty much the inverse of the power rule. So if I want to anti-differentiate a term that's a times x to the n, I need to first increase the exponent by 1, and then divide whatever coefficient you have by that new exponent. And that is our anti-power rule. So if we've got 3x squared plus 1, we'll just take this one term at a time. Increasing the power by 1 will make it x cubed, and then dividing 3 by that new number, 3 divided by 3, is just 1, and we don't really need to write the 1. The antiderivative of 1 is just x. Okay, if you don't see that, it's really like we have 1x to the 0, because x to the 0 is 1. So if we increase this power by 1, and then divide the original coefficient by that new exponent, we just get x. So yeah, we've got x cubed plus x from 1 to 3, divided by 3 minus 1. We might as well just write that as 2. And so now we're going to substitute in both 3 and 1 into that antiderivative and subtract. By the way, this evaluation is given to us with the fundamental theorem of calculus. Okay? The fundamental theorem of calculus has two main parts, and one of the parts is just explaining how we evaluate these definite integrals. So yeah, let's go ahead and do that. We're going to substitute in 3. So 3 cubed plus 3. Then we're also going to substitute 1. So 1 cubed plus 1. Find the difference of those. And then finally divide by 2. So 3 cubed is 27. Plus 3 is 30. So we have 30 minus 1 plus 1 is 2 over 2. 30 minus 2 is 28. And 28 divided by 2 is 14. This problem was an open-ended question. It had no multiple choices, so you will have to bubble in 14. Number 5 says, the graph of the function f of x equals x over 1 plus x squared is shown in the figure above. Which of the following statements are true? And then there's 3 statements about various limits here. And really we need to go through each of these 1, 2, and 3 choices and determine each individual one if they're true. That way we can answer the question. So let's just take them one step at a time. One says the limit of f of x as x goes to negative infinity is equal to the limit of f of x as x goes to infinity. In other words, the end behavior on the left is the same as the end behavior on the right. Now just looking at the graph, it does look like there is a horizontal asymptote at y equals 0, in which case the graph would go to 0. At least from the graph, it does look like 0 equals 0 and that this is true. But we can also tell this from the actual equation itself. Anytime in a rational function where the denominator has a larger degree than the numerator, in this case it's x squared versus x to the first, that will always have a horizontal asymptote of y equals 0. And the horizontal asymptote defines the end behavior and also defines the limit as x approaches plus or minus infinity. So in this case, yeah, we do have a horizontal asymptote, y equals 0. So the limit as x approaches negative infinity and infinity, both limits at infinity should equal 0. And so 1 is going to be one of our answers. Since we can verify that, yeah, this does equal 0, this does check out, we can go ahead and eliminate some of these answer choices, right? Can't be A, because we have at least one of these. Can't be D, because 1 has to be one of the answers. So we've narrowed it down to B, C, and E. Let's take a look at number 2. The limit of f of x as x approaches 0 from the left equals the limit of f of x as x approaches 0 from the right. So when you see these little minus and plus symbols on the top right-hand corner of those limit values, that's saying either from the left or from the right. And this we could just tell visually. Okay, look at the graph. As we approach, here's where x equals 0. As we approach x equals 0 from the left, we are getting closer and closer to 0. Similarly, as we approach x equals 0 from the right, we are also approaching that y value of 0. So both the left and the right hand limits agree, therefore it equals 0, and therefore this is going to be a right answer too. So if our answer choice doesn't have 2, we can eliminate that. That allows us to eliminate C. And so now it just comes down to number 3. The limit as x approaches 1 of this expression does not exist. Now let's go back and just review what the limit definition of the derivative actually is. So a derivative of f of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. There's another way you could write this with delta x as well, but it's going to be basically the same as this. Now, we don't really necessarily need to know this, but we do need to know how to find the derivative at a point and what its limit definition is. So this is just for finding a derivative overall. If we want to evaluate a derivative at a point, not just in general, f prime of, let's call it a, that's going to equal the limit as x approaches a of f of x minus f of a over x minus a. Now take a look at that expression, that limit expression, and compare it. It looks kind of similar, doesn't it? Okay, like if we want to find the derivative at 1, for instance, the limit as x approaches 1 of f of x minus f of 1 over x minus 1. And we can check and verify that f of 1 does equal 1/2. All right, you can kind of see it from the graph, like if up here, f of 1 kind of looks like it's 1/2, but you could also just plug it into x and verify that. 1 divided by 2 is 1/2. So what we have is this exact expression, and really that's what this problem is trying to get you to realize, is that when you have an expression like this is simply asking for the slope at that point. And this particular one says it does not exist. However, we can see clearly the function does have a slope here. It looks like it might be 0 if that does in fact turn out to be the local maximum. But either way, it is going to exist, so this is not going to be correct, and our answer is B. Number 6 says the graph of f double prime, and then it clarifies what that means, although you should know that that means the second derivative. The graph of f double prime, the second derivative of the function f, is shown on the figure above. On what intervals is the graph of f concave up? So really the key to answering this question is understanding what the second derivative tells you about the concavity of f. So let's break it down. If f is concave up, that means the graph is doing something like this. And I'm talking about f here, not f double prime. If f is concave down, then it's making like kind of a sad face. And so when it's concave up, the second derivative will be positive. But if f is concave down, the second derivative is negative. So if I'm looking at this graph and trying to identify when is the second derivative positive or negative, I only need to identify the parts of the graph that are either above or below the x-axis. So from -1 to 3, we can say that f double prime is positive because it's above the x-axis, and everywhere else, from -infinity to -1, and from 3 to infinity, down here, since the graph is below the x-axis, f double prime is negative. So between -1 and 3, since f double prime is positive, that means that the function f is concave up. So our answer here is D. Number 7 is asking for the integral of the product of x minus 1 and the square root of x. So the first thing to think about here is that this problem is going to be a lot easier if we rewrite that expression as sort of like a polynomial. And to do that, we want to reinterpret root x as a rational exponent of x, so x to the 1/2. And so the first thing I'm going to do is I'm going to rewrite this problem as the integral of x minus 1 times x to the 1/2. That way we can use our exponent properties to correctly distribute the x to the 1/2 to both of these terms. So we'll use the distributive property to simplify this. X times x to the 1/2 is going to be x to the 3/2. And that's because whenever you multiply two powers that have the same base, you will add those exponents. So 1 plus 1/2 would be 1.5 or 3/2. X to the 1/2 times -1 would just be negative x to the 1/2. So now that we've written this in sort of a pseudo-polynomial form, we can then just use the anti-power rule. It goes a little something like this. The integral of anything in the form a times x to the n dx will be a over n plus 1. Basically, you increase the exponent by 1, divide the coefficient by that new exponent. So we'll have x to the n plus 1, and then also divide that coefficient by whatever that new exponent is. And then, of course, plus c. So we'll take this one term at a time and find the antiderivative of that expression. So this is going to equal, let's see here, if I need to increase the exponent by 1, I need to add 2 over 2, so that'll be 5/2. Now, the original coefficient here was 1, so you could think about this as like 1 divided by 5/2. But anytime you divide 1 by a fraction, all that really does is just gives you the reciprocal back. So 1 divided by 5/2 is the same thing as 2/5. Minus, if I add 1 to a half, I get 3/2. And then I need to divide by 1 by 3/2, which is the same thing as multiplying by 2/3. Of course, I need that plus c anytime you find an indefinite integral. And so there you go. Our answer is A. Number 8 says, let f be the function defined by f of x equals x cubed minus 6x squared minus 15. At what value of x does f have a relative maximum? So if we're looking for a relative maximum on the graph, we're looking for a point that looks kind of like this. So you'll have a relative max if the function's value is greater than all the points around it. And you'll have a relative minimum if the function's value is smaller than all the points around it. So basically, if you've got a point that is at the top of a hill, it's a maximum, and at the bottom of the valley is a minimum. And so the way we can determine first where those relative extremes are is we need to find the first derivative. The first derivative gives us a function to define the slope of f at any point. And for relative extrema, and that's for maxima and minima, the slope at these points is 0. And so basically what we want to do is first identify where the first derivative is equal to 0, and then we'll find all the maxima and minima, but then we need to break it down a little bit further and find whether or not it's a maximum or a minimum. So I don't want to get too far ahead of myself. Let's first try to identify where the extrema are. To do that, we need to find the first derivative of x. We can use the power rule to do this. We don't need any special tricks or anything. The power rule, just as a little reminder, says that if you're trying to differentiate a term in the form a times x to the n, you're going to bring that exponent down and multiply it by the existing coefficient, so a times n, and then decrease the power by 1. So we'll do that for each term. For x cubed, if we decrease the power by 1, it becomes x squared, and we'll bring that exponent down, so we get 3x squared. The derivative of negative 6x squared will be negative 12x, and the derivative of any constant is 0, so we're just going to leave it like that. So this function defines the slope at any point of f of x. What we're interested in is when is the slope 0? So we'll set this slope equation equal to 0 and solve it algebraically. We can do that by simply factoring out an x, and then setting each factor equal to 0 using the zero product properly. So either x is equal to 0 or x is equal to 4. 3 times 4 minus 12 is 0. These may both be maxima. They may both be minima. You might have one of each, but this is where those relative extrema are going to be. Now, the next part is to identify, okay, we've got these points that might be relative maximum. We can go through and eliminate all the answer choices that aren't 0 and 4, but we need to figure out which one is it. Is it a maximum or a minimum? And to do that, we are going to use one of the two derivative tests. The first derivative test, and you can actually use either one's fine. The first derivative test basically tests to see what's going on with the slope around that point. So if you have a maximum, then the slope is going to be going from positive to negative. If you have a minimum, the slope will be going from negative to positive. So the strategy here, and I'm actually not going to work it out this way, maybe on another problem, because I think the second derivative test is a little bit faster. But what we would do is construct a number line, a little sign chart, and then just plug in values into the derivative to find out whether or not it's positive or negative on either side of 0 or 4. Okay, so that's the first derivatives test. Okay, you're going to make a sign chart and test f prime on either side of 0, but also 4. Okay, we're not actually going to work it out that way. We're going to work it out using the second derivative test. For the second derivative test, we, instead of trying to make a sign chart and plugging in numbers and all that, we are going to find the second derivative And depending on whether or not the second derivative at that point is positive or negative will tell us whether or not it's a maximum or minimum. So if the second derivative is positive, that means that the function f is concave up. And we talked about this in a previous problem, but concave up is going to look something like this. And so that means that point we're going to have a minimum. If we test the second derivative and it's negative, that means that the graph is concave down, and therefore we will have a maximum. So let's find that second derivative, and then we'll test at 0 and 4 and see what's happening. So the second derivative, we can use the power rule once again on that first derivative. The derivative of 3x squared is 6x, and the derivative of 12x is just 12. So we got 6x minus 12. And what we're going to do is we're going to test 0 and 4 and see if we get a positive or a negative answer. Now, if you happen to get 0, then it'll be inconclusive, and so you'll have to fall back on the first derivative test, but this should work for most problems. F double prime, let's start with 0, is 6 times 0 minus 12. 6 times 0 is 0, minus 12 will be negative, so yeah, it'll be negative 12. That means, since it's negative, we have a maximum at 0. Okay, but let's test out 4 just to be sure. F double prime at 4 would be 6 times 4 minus 12. That's going to be 24 minus 12 is a positive 12. So therefore, since it's positive, we have a minimum happening at 4. Since the only maximum that's occurring here is at x equals 0, our answer is C. Number 9 says the acceleration at time t of a particle moving along the x-axis is given by a of t equals 20 t cubed plus 6. At time t equals 0, the velocity of the particle is 0 and the position of the particle is 7. What is the position of the particle at time t? So first we need to understand the relationship between position, velocity, and acceleration. The derivative of position is velocity. The derivative of velocity is acceleration. And you can also work backwards here. The antiderivative of acceleration is velocity. And the antiderivative of velocity is position. Now the function they give us is acceleration, so we'll work backwards to find the position. So let's start with our acceleration function a of t. It's 20t cubed plus 6. To find the velocity, we are going to find the antiderivative of a of t. And this is going to use the anti-power rule. Velocity is the antiderivative of acceleration. So let's figure out what that actually is. Using the anti-power rule, we're going to increase the exponent by 1 and then divide the coefficient by that new exponent. 20 divided by 4 is 5. The antiderivative of 6 is just 6t, and then we have a plus c. Anytime you integrate an indefinite integral, you're going to end up with this constant at the end. And the information they give us is going to help us figure out what that constant is. It says that the velocity at time 0 is 0. Okay, so maybe I'll make a little note here. The velocity at time 0 equals 0. So we can use that to figure out what c needs to be for that function. If v of 0 is 0, so this is 0, when t is 0. And this works out pretty easily because you're just multiplying all of those terms by 0. So it's just going to be 0 equals 0 plus c. And so this implies that c is, well, 0. So that means my velocity function is just 5t to the 4th plus 6t. Now I can use that to find position because position is the antiderivative of velocity. So my position function, which I'll call p, will be the integral of velocity. Now I'm going to use the same anti-power rule that I did before to find position. So the position function will be t to the fifth, and then I'll divide 5 by 5 to get 1, so just t to the fifth, plus t squared, and then I need to divide that coefficient by 2, so 6 divided by 2 is 3. And of course, we've got that plus c. The other piece of information they gave us was about the position. The position at time 0 is 7. So we're going to use that to find the c value for that position function. If this is 7 at time 0, you can see, hopefully pretty easily, that this means that c for this function is 7. That means our position function with respect to time is t to the fifth plus 3t squared plus 7, which is answer choice D. Number 10 says if f of x equals sine of x divided by 2x, then what's f prime? To answer this question, we need to be familiar with the quotient rule. Now, the quotient rule basically tells you how to find the derivative of a fraction, or really just a quotient, which is when you're dividing two functions. So if you've got a fraction or you've got a quotient, now a lot of times you'll see in textbook this written as f over g, but I'm going to write it as t over b for top and bottom. So if we want to find the derivative of t divided by b, top divided by bottom, we are going to multiply the derivative of the top by the bottom and find the difference of that and the product of the top and the derivative of the bottom. T prime b minus tb prime divided by the bottom squared. Let's go back to f of x and identify what's the top, what's the bottom, what are the derivatives of those. The top, in our case, is sine x. The derivative of sine x is one of those that you should just have memorized. It's cosine x. We're not going to get into the proof in this video. The bottom here is 2x, and you can use the power rule to find the derivative of that, which is just 2. And we also need to find b squared. Okay, b squared is going to be 2x squared. In other words, 2x times 2x, so that would be 4x squared. F prime of x is going to be the top, the derivative of the top, that's cosine x, times the bottom, which is 2x, minus the top, which is sine x, times the derivative of the bottom, which is 2, divided by the bottom squared, which is 4x squared. Now, if you're looking at all this and you look at your answer choices, none of them look exactly like this. And that's because we have a factor of a 2 that can be reduced here. If we factor out a 2 as a GCF from the numerator, 2 times cosine x minus, times x, minus sine x over, and let's go ahead and just factor out a 2 here, even though you might be able to do that without actually writing it like that, at 2x squared, because 2 times 2 is 4. Now we see that we've got that factor of 2 that we can reduce to 1 and write our final answer here for f prime x, which is the derivative of f, x cosine x minus sine x over 2x squared. So our answer here is B. Number 11 says the piecewise linear graphs of the functions f and g are shown in the figure above. If h of x is the composition of f and g, what is the value of h prime 3? What this question is asking for is the value of the derivative of this other function h at x equals 3. Before we start this problem, though, let's highlight each of the graphs to make sure we're referring to the correct one. I'll highlight f of x in yellow, and I'll highlight g of x in green. To answer this question, we are going to need to take advantage of what's called the chain rule. The chain rule is what we use to differentiate a composite function, so that if we have a function in the form f of g of x, where you have one function embedded within another function, If we want to find the derivative of that, we first need to differentiate the outside function f, leaving the g of x inside there, and then multiply that by the derivative of that inside function g. So since h is defined as f of g of x, we can say that the derivative of h is f prime g times g prime. Specifically, this question is asking for the derivative of h at x equals 3. So I will replace every instance of x with 3. Next, we'll start evaluating whatever we can. And I'll start with this g of 3. This is simply asking for the value of function g at x equals 3. So x equals 3 is right here. Recall that g is the green function. And so we've got something that's not super obvious, but it's a little bit more than 1. We really don't need to know anything beyond that. So I'm just going to say it's approximately 1.2. Next, we need to find the slope of g at 3. So when I calculate the derivative of g at 3, what that's really asking for is the slope of function g at 3. So what we need is the slope of this segment right here. Well, the change in y, our rise, is 4, and our run, or our change in x, is 3. So the slope of that segment is 4 over 3. Now we need to evaluate f prime at approximately 1.2. Hopefully you can see once I draw this arrow why it doesn't really matter if we put 1.2 or 1.3. Either of those estimates will work. Really, any number between 0 and 5 will work because f is a linear function. The rate of change is constant throughout the entire segment. The slope of f at x equals approximately 1.2 is negative 1. So h prime at 3 will be negative 1 times 4/3, which is negative 4/3. So our answer is B. Number 12 says, what is the limit as h approaches 0 of cosine of pi over 2 plus h minus cosine of pi over 2 all divided by h? This problem looks like a complicated limit problem, but is actually a derivative problem in disguise. In order to be successful with this problem, you need to be familiar with the limit definition of the derivative. If you want to find f prime x, which is the derivative of f at x, we want to find the limit as h approaches 0 of f of x plus h minus f of x over h. Now take a moment to look at what I just wrote and compare it to the original problem. It looks pretty similar. And that's because in this problem, we are trying to evaluate the derivative of cosine x at pi over 2. So to solve this problem, this is going to equal the derivative of cosine x at x equals pi over 2. One of the derivatives that you just need to know is cosine. There are several transcendental functions like e to the x, the natural log of x, sine of x, cosine of x, where you're just expected to know what those derivatives are. The derivative of cosine x is negative sine x. And so if we want to evaluate the derivative of cosine x at pi over 2, then this will equal negative sine of pi over 2. Here, you're just going to have to be familiar with some key angle measures around the unit circle to be able to evaluate sine of pi over 2. This is just another one of those little facts that you're just expected to know. So just as a little reminder, the unit circle is a circle with radius 1, centered at the origin. And it's useful in evaluating trig functions. The points along the circumference of the circle give us cosine and sine values. 0 radians is here. Pi over 2 radians, which is equivalent to 90 degrees, would have a terminal side along the positive y-axis. pi radians is equivalent to 180 degrees, and 3 pi over 2 radians is equivalent to 270 degrees. If you go all the way around at 360 degrees, that's equivalent to 2 pi radians. So if I want sine of pi over 2, I'm going to be looking at the point where this terminal side of pi over 2 intersects with the unit circle. There's going to be an x-coordinate and a y-coordinate, and since this circle has a radius of 1, the x-coordinate is 0 and the y-coordinate is 1. For any point on the unit circle circumference, the x-coordinate corresponds to the cosine value of the angle measure in question. The y-coordinate corresponds to the sine value of the angle measure. So sine of pi over 2 is 1, and since it's negative sine of pi over 2, this equals negative 1. Our answer is B. Number 13 says, if x squared plus y cubed is x cubed times y squared, then what is dy dx? In other words, what's the derivative of y with respect to x? If you ever get a question like this where y is not isolated and there doesn't seem to be any easy way to isolate y, typically these problems can be handled using a technique called implicit differentiation. And what that means is we can find the derivative with respect to x of both sides of the equation, and using the chain rule should be able to find a dy dx within that next statement. So let's take the original equation, x squared plus y cubed equals x cubed times y squared, and start to differentiate both of these sides with respect to x. On the left-hand side, we'll start by differentiating x squared with respect to x, and we get 2x. This is using the power rule. What's a little bit harder, I think, to remember is how to find the derivative of an expression involving y when you're differentiating with respect to x. And to do that, you actually have to use the chain rule. Now, we kind of did use the chain rule with the x squared, but the inside function is x, and the derivative of x with respect to x is 1. So really, there's like a times 1 here that you wouldn't normally write. But with y, when we find the derivative of y with respect to x, dy dx is not 1. So when we differentiate this, we're going to use the power rule, 3y squared, but then due to the chain rule, we need to find the derivative of y with respect to x. And that's where that dy dx is going to come from. Then on the right-hand side, we'll have to use the product rule. The product rule has us multiply the first function, in this case, x cubed. The derivative of that is 3x squared times the second function plus the original first function times the derivative of the second, which through the power rule and the chain rule is 2y times the derivative of y with respect to x. Now our goal here is to find dy dx, so we're going to have to algebraically isolate that from everything else. To do that, we want to bring all the terms that have a dy dx, and there's only two of them, over to one side, and bring all the other terms to the other side. So the 3y squared dy dx is already on the left-hand side, but let's bring that x cubed times 2y over there as well. So I've got that 3y squared dy dx minus x cubed times 2y. I'm just going to rewrite that ever so slightly as 2 times x cubed y dy dx. And then the other two terms should be over on the right-hand side. The 3x squared y squared is already over there, but if we subtract 2x from both sides, we can get that other term over to the right-hand side. Next, we're going to factor out the dy dx, which is what we're actually trying to find, as a GCF, or a greatest common factor, from the left-hand side, kind of like using the distributive property in reverse. So I'm going to factor that dy dx out of each term, leaving me with this expression. For now, I'm going to leave that right-hand side alone. Finally, to get the dy dx by itself, I need to divide both sides of the equation by this entire expression here, the 3y squared minus 2x cubed y. So if I divide both sides by that expression, I'll have the dy dx by itself, and on the right-hand side, I'll have 3x squared, y squared minus 2x, all over what I'm dividing by, which is 3y squared minus 2x cubed y, and we can see that our answer is C. Number 14 says, for which of the following functions does the third derivative of y with respect to x equal the first derivative of y with respect to x? And we have three options, e to the x, e to the negative x, and sine x. As we go through this problem, you are going to need to be familiar with the derivatives of certain transcendental functions. So e to the x, sine x, cosine x, these are functions that you just need to know what the derivatives are. So let's go through and find not just the first, not just the second, but all three derivatives for each of these three functions. And what we're looking for is, for which one of these is the first derivative equal to the third derivative? So let's start with e to the x. Now e to the x is kind of a nice function because it is its own derivative. So the first derivative of e to the x is e to the x. The second derivative of e to the x is e to the x. And then the third derivative is also e to the x. You could take as many derivatives as you want. It's still going to be e to the x. Since the first derivative is equivalent to the third derivative, we're going to include 1 in our final answer here. So we can eliminate choice B, choice C, and choice E right off the bat. Now let's look at e to the negative x. Here we'll have to use the chain rule. So we need to differentiate e to the negative x, which would be itself, but then we need to multiply by the derivative of the exponent of e. So we need to differentiate negative x. The derivative of negative x is negative 1. So we need to multiply by negative 1. Now let's do that again. We need to differentiate negative e to the negative x. Well, e to the negative x derivative is once again e to the negative x times negative 1. We already have a negative 1 there, so it's negative 1 times negative 1, which is just positive 1. So the second derivative of e to the negative x is e to the negative x. Then we'll differentiate one more time. And we've already done this one. It's the one we did at the beginning. So we should know that the derivative of e to the negative x is negative 1 times e to the negative x. This is another one where we can see that the first derivative is the same as the third derivative. So that one checks out as well. So we know 1 and 2 are both correct. That leaves us with choice D. We know that to be right. Although if you have time, it might be worth double checking that one just to make sure that its first derivative is not the same as the third derivative. So the first derivative of sine is cosine. This is one of those transcendental functions where you're expected to know what the derivative of that is. The same thing goes for cosine. The derivative of cosine is negative sine. And finally, we need to take the derivative of negative sine, which is negative cosine. Here, the first and third derivatives are not the same. One's positive, one's negative. So that tells us that D definitely is the right answer. Number 15 says, what is the limit of 2x divided by the absolute value of x as x approaches 0 from the left? This is a one-sided limit problem, so we don't need to worry about whether the left and the right-hand limit are equal. We're only trying to find the left-hand limit. With functions that involve a fraction where you have an absolute value on one of the sides, I think it's easiest to approach these problems from a graphical perspective. Now, you might not know off the top of your head what this graph looks like, but you can start to plug in values for x to get a good idea of what the graph looks like. For instance, if we plug in 1, we get 2 times 1, which is 2, divided by the absolute value of 1, which is 1. 2 divided by 1 is 2. If we plug in 2, we get 4 over 2, which is also 2. If we plug in 3, we get 6 divided by 3, which is also 2. And it shouldn't take long for you to realize that no matter what positive number you substitute in for x, you're going to get 2. Now, we can't substitute in 0 because we can't divide by 0. So we're definitely not going to have a value here, but for every positive number, the value of the function is 2. If we start to plug in negative numbers, we have a different result, because when we take the absolute value of something, it makes whatever the input was positive. Absolute value is a function that outputs the positive distance that number is away from 0. In other words, if you input a positive number into the absolute value, nothing changes. It will output that positive number. But if you input a negative number into an absolute value function, it will report back the positive version of that number. For instance, the absolute value of -5 is positive 5. So if I try to substitute in -1, for instance, in the numerator I get 2 times -1, which is -2, but in the denominator I get positive 1. So -2 divided by positive 1 is -2. If I substitute in -2, I get -4 divided by 2, which is -2. Substituting in -3 will also give me -2, and it shouldn't take long before you realize every negative number that you input into this function will output a -2. So our graph looks like this. It's a classic jump function, which has a non-removable discontinuity due to this jump. Now, if we're asked to find the left-hand limit, what that's referring to is the value that the function is approaching as x approaches 0 from the left. So if we follow this function from the left and get closer and closer to 0, we can see that the function is approaching and really equals along the entire function -2. A limit is not asking for the actual value at x equals 0. That would be undefined. It's asking for what the limit is approaching. Now, just to give you a little bit more detail on this question, the limit as x approaches 0 from the left, the whole from the left thing is notated with that little minus sign in the upper right corner of the 0. If we were interested in the limit from the right, it would look like this. The limit as x approaches 0 from the right with a little plus in that superscript area. And if we look at the function from the right, we can see that the function is approaching a y value of +2. Now, if the question was just asking what's the limit as x approaches 0 overall, not one of the one-sided limits, but just as a whole, we would say that does not exist, because the left and the right-hand limits must be equal for the limit to exist. Number 16 says, which of the following statements about the curve y equals x to the fourth minus 2x cubed is true? All of the answer choices have to do with the number of relative extrema and points of inflection. To answer this question, we need to understand what those are and how to find them. So let's start with relative extrema. Relative extrema is a catch-all term for both maxima and minima, and you can find maxima and minima on a function anywhere where you find the derivative changes sign. For example, a maximum point on the graph might look something like this. Notice how the graph changes from having a positive slope to a negative slope. So anywhere on the graph where we have a sign change of the slope or a sign change in the derivative, we will be able to identify a relative extrema. Points of inflection are found similarly. For points of inflection, we need to find the second derivative, and we are also looking for a sign change on that second derivative. Points of inflection are points on the graph where the concavity changes. To sum this up, Relative extrema are points where the sign of the derivative changes, and points of inflection can be found anywhere the sign of the second derivative changes. So let's start with the first derivative. The function, and I'll just go ahead and rewrite it, y equals x to the fourth minus 2x cubed, can be differentiated using the power rule. Y prime will be 4x cubed minus 6x squared. We are looking for where the sign of this function changes. You can find sign changes either where the derivative equals 0 or undefined, but this function, this y prime, is a polynomial, so it'll never be undefined. So we really just need to find where it's equal to 0. To do that, we are going to factor out an x squared as a greatest common factor and set each of these two factors equal to 0 using the zero product property. We have a point x equals 0 and another point x equals 3/2 where we have a potential relative extreme. We do need a test to make sure that the sign is actually changing at these values. It is possible that the sign does not change when you find a critical value like this. To map this out, I'm going to just draw a number line for y prime. I'm going to plot the critical values, 0 and 3/2, and then consider whether or not y prime is positive or negative in between and outside of these values. So for example, if I substituted a number like -2 into y prime, and it might be easier to use the factored version, I will end up with a negative number. So between -infinity and 0, the function's negative. And when I say the function, I mean the derivative of y is negative. Between 0 and 3/2, I can pick a number like, say, 1, and if I substitute that into y prime, I'm going to get a negative number. So notice we do not have a sign change at x equals 0. What might be happening on the graph of y is we have a negative slope and then a negative slope after the slope becomes 0. So in that case, that would not be a relative extreme. Now, if I pick a number like, let's say 5, some number that's bigger than 3/2, and substitute that into y prime, I'm going to end up with a positive value. So notice here we do have a sign change at 3/2. Specifically, the sign is changing from negative to positive. So if on the graph of y, the slope changes from being negative to positive, it doesn't ask us what kind of extreme this is, but we definitely know that it is a relative minimum. Either way, there is only one relative extreme value. So we can eliminate some of these answer choices. A says there is no relative extremum. That's not right. D says there are two relative extremas, so it's not going to be D. And E has 3 relative extremas. That's not going to be the case also. So it's really just between B and C, and so we need to determine whether there is one point of inflection or two. To find the number of points of inflection, we're going to do exactly the same thing that we just did, except with the second derivative. So we'll differentiate y prime and the derivative of y prime using the power rule once again. Y double prime is 12x squared minus 12x. To find those points of inflection, we're looking for a sign change on y double prime. So we need to find what I'll call the subcritical values of the function, which will be where the second derivative equals 0 or undefined. But just like with y prime, this is never going to be undefined because y double prime is a polynomial. So we're really just looking for where it equals 0. If I factor out an x from this expression, I'll have 12x minus 12, and that gives me a subcritical value at 0 and another subcritical value at 1. So just like I did with the previous one, I'm going to construct a little number line chart here with 0 and 1, and I'm going to test the values by plugging them into x for y double prime to see in these intervals whether the function is positive or negative. So if I plug in a negative value in here, for example, if I plug in -2, I will end up with a positive value for y double prime. If I substitute in a number like 0.5, I get a positive times a negative, which is negative. If I substitute in a number like 5, I'll get a positive times a positive, which is positive. So notice here how we have two sign changes. We have a sign change at 0 and a sign change at 1. Therefore, there are 2 points of inflection, and our answer is C. Number 17 says, if f of x equals x times the square root of 3x squared plus 1, then what is the derivative of f? To answer this question, you need to know the product rule, the chain rule, and also that the square root of something is equal to that something to the 1/2 power. So before we start this problem out, let's rewrite the function. Instead of using the radical symbol, I think it'll be easier if we rewrite it as a rational exponent. F of x equals x times 3x squared plus 1 to the 1/2 power. Now, like I said earlier, we're going to need the product rule here. X is the first function. 3x squared plus 1 to the 1/2 power is the second function. So as I try to differentiate this equation, I'll have the derivative of the first, which is 1, times the second, so that's times 3x squared plus 1 to the 1/2, plus the first function, x, times the derivative of the second. This is where the chain rule comes into play. We'll use the power rule and bring down that exponent as 1/2 times 3x squared plus 1 to the power of negative 1/2. But then with the chain rule, we need to multiply this by the derivative of the expression inside the parentheses there. So the derivative of 3x squared plus 1 is just 6x. Now before I start going any further, I'm going to try to clean this up and make it a little bit easier to read. F prime of x equals 3x squared plus 1 to the 1/2 power plus 1/2 times 6 is 3, x times x is x squared. So 3x squared times 3x squared plus 1 to the negative 1/2 power. Now this is our answer, but if you look at all the answer choices, none of them really look exactly like this. And that's because all of the answer choices, except for E, have the answer written using that radical symbol. So we're really going to have to go back and rewrite this expression, even though we've already found the derivative, using that radical symbol. So let's start to rewrite these with radicals. Whenever you raise something to the 1/2 power, that's equivalent to taking the square root of it. Over here, we've got 3x squared times 1 over the square root of 3x squared plus 1. We can combine those two factors as 3x squared over the square root of 3x squared plus 1. And now our expression is starting to look a little bit more like what we see over to the left. There's one little catch here, though, and that is we are going to need a common denominator to combine these two fractions. It doesn't really look like the first square root is a fraction, but we can think of it as being over 1. The common denominator is the square root of 3x squared plus 1. So we need to multiply both the numerator and the denominator of that first fraction by the square root of 3x squared plus 1. Now the expression in that square root is 3x squared plus 1. That we see that already in the numerator on that left-hand fraction. You can see it here. So when we do multiply the top and the bottom by that root 3x squared plus 1, multiplying it on top is simply going to get rid of that square root. If I have the square root of x times the square root of x, that gives me the square root of x squared, which is just going to give me x. So the numerator of that first fraction is just going to be 3x squared plus 1. We'll have that denominator root 3x squared plus 1. The second fraction will be still 3x squared divided by the square root of 3x squared plus 1. We have our common denominators, so we can combine them now. 3x squared plus 1 plus 3x squared. We've got two like terms there, the two 3x squareds. So that'll become 6x squared plus 1 over the square root of 3x squared plus 1. And we see that our answer is D. Number 18 says, let f be the function defined by that piecewise function. Which of the following statements about f are true? And then there are three statements about this function. 1 says that the limit as x approaches 5 exists. 2 says f of 5 exists. And 3 says f of x is continuous at x equals 5. I think it might be easiest to sketch a diagram of the graph of this function, just so you can get a better idea of whether or not these statements should be true. Whenever you try to evaluate a limit, it's always best to try to use direct substitution. If we try to find the limit as x approaches 5, we plug in 5 into x, but you're going to see that that's not really going to work here because we get 0 over 0. However, even though we get something that's undefined here, and that doesn't really help us find the limit explicitly, whenever you get 0 over 0 through direct substitution, more than likely that's going to indicate that we have a hole in the graph. Now that doesn't mean that's true every time. For instance, if you have an absolute value function, but if it's just a regular old rational function like this, if you get 0 over 0 through direct substitution, that means you have a hole or a removable discontinuity at x equals 5. So we can remove that removable discontinuity by rewriting x squared minus 25 over x minus 5 as x plus 5 times x minus 5 over x minus 5, and watch as the x minus 5s will reduce to 1. Y equals x minus 5 is a linear function, meaning the graph has a y-intercept of 5 and a slope of 1. Essentially, it's going to look something like this. Now, that would just be the rational function itself, but there is a hole that exists at x equals 5, so let's make sure we include that hole in our sketch. That open dot is indicating the function does not have a value there. Now, this is a piecewise function, so when x is 5, we're actually not going to use that function at all, which is good because it's not defined there, but rather, we are going to define the function to equal 0. So when x equals 5, y is 0. We've got a point way down here. So now let's go through the different statements and see if we can identify which are true and which are false. 1 says the limit as x approaches 5 exists. In order for the limit to exist, the left-hand limit has to equal the right-hand limit. And you can see on the graph that the left-hand here limit is 10, and the right-hand limit is also 10. So since the left-hand limit equals the right-hand limit, then the limit exists. F of 5 also exists. In fact, it's explicitly defined in the function itself. F of 5 is 0. So that is true. 3 says f of x is continuous at x equals 5. Now, hopefully you can see on the graph why this is not going to be true, but we can say that it's not true based on the definition of continuity. In order for a function to be continuous at a certain x value, the value of the limit needs to equal the value of the function. Now notice here that the limit as x approaches 5 is 10, but the value of the function is 0. So this is not going to be true Therefore, the function is not continuous at x equals 5. You can also just tell based on the graph, if there's at any point on the graph where you'd be unable to draw that graph without lifting your pencil, then the function is not continuous there. So because 1 and 2 are the only true statements, our answer is D. Number 19 says, what is the average rate of change on the function f defined by f of x equals 100 times 2 to the x on the interval 0 to 4? To answer this question, we need to know how to compute the average rate of change of a function on an interval. Let's first talk about what that means. This function, 100 times 2 to the x, is an exponential function that more or less does something like this. I'm not going to put too many numbers on this. Really, you don't need to know what the graph looks like, but I think for this explanation, it'll really illustrate how you find this. So if we want to find the average rate of change from 0 to 4, x equals 0 would be here, x equals 4 would be somewhere out here. That's about all the labeling I'm going to do. We want to find the average rate of change or the average slope between these 2 points on the function. So if I plot those 2 points and draw a line that passes through them, this is a secant line rather than a tangent line, the slope of that line is the average rate of change. So to answer this question, all you need to do is use your classic slope formula. So the slope of this secant line, so the slope of the secant line is equal to f of b minus f of a over b minus a. You might be more familiar with this formula in the form y2 minus y1 over x2 minus x1, but at the end of the day, it's still the same formula. What we need to do is compute the value of this function at both 0 and 4. So f of 4 minus f of 0 over 4 minus 0, we need to calculate what is f of 4 and f of 0. So if f of x is 100 times 2 to the x, f of 0, let's start with that one, would be 100 times 2 to the 0th power. Anything, aside from 0, raised to the 0th power is 1, so 100 times 1 is just 100. F of 4 would be 100 times 2 to the 4th. Now, 2 to the 4th would be 2 times 2 times 2 times 2. That's 4 2s, so that's 16. 100 times 16 is 1600. So now let's go ahead and substitute in those values. 1600 minus 100 over 4 minus 0. Let's go ahead and compute that. That's 4. 1600 minus 100 is 1500 divided by 4, and 1500 divided by 4 is 375. So our answer is B. Number 20 says, if the integral from 0 to 1 of the nth root of x minus x to the nth power dx equals 3/4, then what is the value of n? To solve this, we need to anti-differentiate this expression so that we can integrate it from 0 to 1. So to do that, we need to use the anti-power rule, which is really just the power rule in reverse. To make that a little easier, I can rewrite the nth root of x as x to the 1 over nth power minus x to the n. Generally speaking, when you have a term that's in this form and you're trying to anti-differentiate it, you're going to increase the exponent by 1 and then divide by whatever that new exponent is. Another way of thinking about dividing by a plus 1 in this case would be by multiplying by the reciprocal of a plus 1. So if our exponent is 1 over n on this first term, then the antiderivative of that would be x to the power of 1 over n plus 1, and then that whole term divided by 1 over n plus 1. So 1 over n plus 1 would be its coefficient, minus Now the anti-power rule will work a little bit simpler with x to the nth. Going to increase that power by 1 and then divide by n plus 1. Now we do need to evaluate this integral from 0 to 1, which means we need to substitute in 0 and substitute in 1 and then subtract those two values. Now be careful on what you're substituting these numbers into. We want to be substituting them for x, not for n. We are trying to solve for n. So let's start by substituting 1 into everywhere where we see x. So 1 over n plus 1 times 1 to the 1 over n plus 1 minus 1 over n plus 1 times 1 to the n plus 1. And then we'll subtract the exact same expression, but with 0 substituted in to x. The theorem that allows us to do this is called the fundamental theorem of calculus. So we're going to subtract 1 over 1 minus n plus 1 times 0 to the power of 1 over n plus 1 minus 1 over n plus 1 times 0 to the n plus 1. All of that still equals 3/4. Now we've got a lot going on here, but luckily this is going to simplify pretty nicely. Let's go through and see what we can get to simplify. Let's start with the zeros. 0 to any power is 0, except for 0, of course. So this whole term right here just simply equals 0. Also, this second term just equals 0. So this entire second expression is just 0. From here to here is just 0. On that first expression with the ones, 1 to any power is just 1. So 1 to the 1 over n plus 1 is 1, and 1 to the n plus 1 is also 1. So this term right here is 1, and so is this. 1 times anything is just the anything, so that just simply leaves us with 1 over n plus 1 minus 1 over n plus 1. Remember, these are just being multiplied by 1, and we don't need to write that. So that equals 3/4. So we need to combine the two fractions. To do that, we need a common denominator. And I think it might be easier to do this if we take that first fraction, which has a fraction in the denominator, and try to simplify it in a way so that there are no fractions inside of sort of the overall big fraction. So I'm going to do a little scratch work out to the side to kind of get us there. 1 over n plus 1. We're going to try to find a common denominator in that denominator and rewrite the 1 right here as n over n. Then we can pull those two fractions together to get 1 plus n over n. And then since division is simply multiplication of the reciprocal, we can rewrite this as 1 times n over n plus 1, which just equals n over n plus 1. So I'm going to rewrite what I've got highlighted in yellow there as n over n plus 1. And that actually gives us, sort of unintentionally, but does give us the common denominator that we're looking for. So now we can combine those two fractions to get n minus 1 over n plus 1 equals 3/4. And from here we can use the cross products property to cross multiply 4 by n minus 1 and multiply 3 by n plus 1 and set those two products equal together. That is called the cross products property that lets us do that. We have 4 times n minus 1 equals 3 times n plus 1. Using the distributive property, we get 4n minus 4 equals 3n plus 3. We can subtract 3n from both sides to get n minus 4 equals 3, and then add 4 to both sides to get n equals 7. And that is our answer. This was not a multiple choice question. it was simply asking for the value of n, so you'd have to bubble in or select that answer specifically. Number 21 says, if f of x is equal to arctangent of pi times x, then what is the derivative of f when x equals 0? Or what is the instantaneous rate of change of f when x equals 0? One thing to note here is that arctangent is the inverse of tangent. There are two different ways that you might see this function notated. One of them is just arctangent, like you see here. Another way is if you see tangent with a little -1 right here, this would mean the exact same thing. To solve this problem, you need to know what the derivative of arctangent is. This is just one of those transcendental derivatives that you need to be familiar with. The derivative of arctangent x is 1 over 1 plus x squared. As long as you know that and you know how the chain rule works, you should be able to answer this question without too much trouble. First, we'll take the derivative of the function f prime x, or the derivative of f of x, equals, using the chain rule, 1 over 1 plus pi x squared times the derivative of pi x, which is just pi. Then we'll evaluate this at x equals 0, so we need to substitute in 0 wherever we see x. Now we can simplify and evaluate. 1 over anything times 0 is 0, so we just have a 1 in the denominator there, and 1 times pi is pi, so the derivative of f at x equals 0 is pi. Our answer is E. Number 22 says, consider a rectangle in the xy plane with its lower left vertex at the origin and its upper right vertex on the graph of the square root of 6 minus x as indicated in the figure above. What is the maximum area of such a rectangle? To find the maximum of a function, you need to first find its derivative, set it equal to 0, solve for x, and then verify that it is indeed a maximum. So let's go through that. We need to first write a function for the area. In general, the area of a rectangle is the length times the width. And in this case, the length is x, the distance from here to here, and the width is the value of the function at that particular x value, which we can say is the square root of 6 minus x. So now we have this function to give us the area in terms of x. To find its maximum, we need to first find the first derivative, and to do that, we'll need to use the product rule, with the first function being x and the second function being the square root of 6 minus x. So let's differentiate. The derivative of x is 1 times the square root of 6 minus x plus x times the derivative of 6 minus x. This will be a little bit easier to do if we think of root 6 minus x as 6 minus x to the 1/2 power. Then we can just use the power rule and the chain rule to come up with this derivative. So the derivative of the square root of 6 minus x is this expression that we've written here. We can also simplify this a bit so that we can evaluate it, which we may have to do later. So this would be 1 over 2 times the square root of 6 minus x times -1. So this whole thing would be negative. So the derivative of the square root of 6 minus x is negative. And since we're multiplying, I'm going to change that plus to minus 1 over 2 times 6 minus x. We can simplify this a little bit 1 times anything is just whatever you have, so we can rewrite this as the square root of 6 minus x times 1 is x, so we can write this as x over 2 times the square root of 6 minus x. I'm going to erase this work that I had down here to give me more room to do the next part. Now we have the derivative for the area function, and to find any relative max or relative minimum, we need to set this function equal to 0 and then solve. This is going to give us a critical value of the area function, so we will have to test it, but if there's only one critical value, which I think there may be on this one, we can rest assured that that has to be our answer. First, I'll add x over 2 times root 6 minus x to both sides. Then I can multiply both sides by 2 times the square root of 6 minus x. That'll give me 2 times the square root of 6 minus x squared, which is just 6 minus x. Using the distributive property, I get 12 minus 2x on the right-hand side. I can add 2x to both sides to get 3x equals 12, and then divide both sides by 3 to get x equals 4. Now don't be too quick to circle B here. The question is asking, what is the maximum area? And what we just found was the x value that gives us the maximum area. 4 is not the area itself. Recall that 4 is just the length. So if we were to draw the rectangle that had the maximum area, the length would be 4, and the width would be the square root of 6 minus x. So going back to our area equation that we wrote up here, if we let x be 4, a of 4 will be 4 times the square root of 6 minus 4, which is 4 times the square root of 2, and now we have the maximum area. Our answer is D. Number 23 says, let f be the function defined above, where a is constant. The function is a piecewise function, where f of x equals 2x minus 4 for all x values less than a, and x squared minus 2x minus 1 for all x values greater than or equal to a. For what values of a, if any, is f continuous at x equals a? In order for f to be continuous at x equals a, we need the value of the function at x equals a to equal the limit of the function as x approaches a. In other words, the value of the function must equal the value of the limit at a. This is the definition for continuity at a point, and so we need to verify that this is true. So let's first look at the limit piece of this equation. In order for that limit to exist, the left-hand limit must equal the right-hand limit. In other words, the limit as x approaches a from the left for f of x must equal the limit of f of x as x approaches a from the right. Now, as we approach a from the left, we will be using 2x minus 4, since that's how the function is defined for values less than a. The limit as x approaches a from the left will equal 2a minus 4. The limit as x approaches a from the right will use x squared minus 2x minus 1, so that limit will equal a squared minus 2a minus 1. This is a quadratic equation that we can solve using properties of equality and factoring. So first, I'll subtract 2a from both sides to get negative 4 equals a squared minus 4a minus 1, and then I can add 4 to both sides so that I get this quadratic equal to 0, like you would for solving any quadratic. This quadratic is factorable, and we can factor it out as a minus 3 times a minus 1, which gives us two potential a values here, a equals 3 and a equals 1. Our answer is D. Number 24 says, let f be the number of trees in a forest at time t in years. If f is decreasing at a rate given by the equation df dt equals negative 2f, and if f of 0 equals 5,000, then what is f of t? To solve this, we need to separate the variables. We need to bring our f's to one side and our t's to the other side. To execute this technique, I'm going to just start by rewriting the original equation and then bring all the terms that have f to one side and t to the other side. So I'll divide both sides by f to get df divided by f, or df times f to the negative 1. And on the right-hand side, multiply dt to get negative 2 dt. Now let's integrate both sides of this equation. The left-hand side will be integrated with respect to f, and the right-hand side will be integrated with respect to t. The antiderivative of 1 over f will be the natural log of the absolute value of f, and there should be a plus c here, but I'm going to implicitly combine it with the plus c that we'll get on the right-hand side. You can just subtract that constant and combine it with the constant that we get over on the right-hand side and just write it as a single constant. So the antiderivative of negative 2 will be negative 2t, and this is where I'll include that plus c. Now I need to get rid of that natural log, and to do that, I can exponentiate both sides of this equation using Euler's number as the base. So if I raise Euler's number to the natural log of the absolute value of f, that just gives me the absolute value of f. And if I do the same thing on the right, nothing is really going to simplify here. I'm just going to have Euler's number to the negative 2t plus c. Now, one thing we can do here is notice that we have an exponential function on the right-hand side. That is going to be positive, so we can drop the absolute value symbols and just be left with f equals. And then one other thing that we can do here to simplify this equation is to rewrite this e to the power of negative 2t plus c as e to the negative 2t times e to the c. We can do that because of our exponent property that says if you've got two powers with the same base and you want to multiply those two powers together, you simply can add those exponents. And we're using that property backwards here. And one reason for doing that is that e to the c to the some constant power is still going to be a constant. If I raise a constant to another constant power, that's just going to be some other constant. I'm just going to rewrite e to the c as c, knowing that it's just some constant. So I'm going to rewrite this equation as f equals c times e to the negative 2t. Now we have our equation for f, but we need to find what that c value is. And to find that, we're going to use the initial condition that f of 0 is 5,000. So if f of 0 is 5,000, then at least in this case, f would be 5,000. C is what we're trying to solve for. And then we have e to the negative 2 times 0, with t being 0. Now, negative 2 times 0 is 0, and e to the 0th power is 1, so that means that 5,000 must be c. So now we have our final equation for f, which is 5,000 times e to the negative 2t, and so our answer is B. Number 25 says, let f be the function defined by f of x equals the square root of x. Using the line tangent to the graph of f at x equals 9, what is the approximation of f of 9.3 equals the square root of 9.3? In other words, we're going to use a little bit of calculus to estimate the value of the square root of 9.3. Also notice there are no answer choices for this problem. A few of the questions on the actual CLEP test will not give you multiple choices. You'll have to solve it and bubble in whatever numerical answer you get. So first, before we start going through the problem, I just like to cover conceptually what it is we're doing here. So if we can visualize the graph of the square root of x, which is 1/2 of a parabola that's been turned over on its side, we are going to use a line tangent to this graph at x equals 9. This line might look something like this to estimate the value of f of 9.3, which would be very close to it. Now, as you can see on the graph, the points right around x equals 9 on that tangent line, if we're looking, somewhere around here, are going to be very close to the points that are on that square root graph, which makes this technique very useful. We won't have to know any special algorithms for calculating square roots or anything like that. We just need to know how to find the equation of this tangent line and then substitute in 9.3 into that and use that as our approximation. We wouldn't want to use this line for any points that are too far away from x equals 9. Like this, whatever equation we get for that tangent line would not be particularly useful for estimating, say, the square root of 12 million or anything like that, because those values are just too far away, and the gap between the tangent line and the curve square root of x gets wider and wider as we move x towards infinity. But right around x equals 9, the points are pretty close, so we can go ahead and use it. To come up with the equation for that line, we are going to use point-slope form of a linear equation. The point-slope form of a linear equation is y minus y1 equals m times x minus x1. We will need the point of tangency, where that line is tangent to the curve, and we'll also need the slope of that tangent line. Now the point should be pretty easy to find because it is the same as the point on the square root of x. And since we're interested in x equals 9, the square root of 9 is 3. So the y coordinate of that point is 3. The point that we're going to use in that point slope form then is 9, 3. Next, we need to find the slope of that tangent line. And to do that, we're going to need to differentiate f of x. F prime, or the derivative of f, represents a function that gives you the slope of f at any x value. So if we rewrite f of x as x to the 1/2 power, we can use the power rule to find f prime x, or the derivative of f of x, which would be 1/2 x to the negative 1/2, or if we want to rewrite it using the square root, would be 1/2 times the square root of x. So if I need the slope of the curve, which will be the same as the slope of that tangent line at x equals 9, I can simply plug in 9 into that equation and get 1/2 times 3, which is 1/6. So the slope of that tangent line is 1/6. Now we have an equation for that tangent line. Y minus 3 equals 1/6 times x minus 9. Now that we have that equation, we can use it to approximate f of 9.3 by simply plugging in 9.3 into x and solving for y. So let's go ahead and do that. Y minus 3 equals 1/6 times 9.3 minus 9. 9.3 minus 9 is 0.3, and now we need to multiply that by 1/6. Here we've got a terminating decimal times a fraction which does not have a terminating decimal, so we're really going to have to convert that to a fraction to get the exact value. 3/10 is equal to, well, I guess the way you read it is what it is, 3/10. So y minus 3 equals 1/6 times 3/10, which is 3/60. Or if we reduce that, 1/20. I'm going to rewrite this equation so it looks a little nicer, and then I'm going to add 3 to both sides. So I have y equals 1/20th plus 3, which would be the same as 1/20th plus 60/20ths. So y would be 61/20. Now, depending on how the answer sheet is set up, if you're lucky, you'll be able to just go ahead and write out this fraction. But if you have to convert it to a decimal, then we're going to have to do a little long division. So if we need the decimal, we need to divide 61 by 20. 20 goes into 61 3 times. 3 times 20 is 60. Subtract, put a little decimal there, bring down the 0. 20 does not go into 10, so we'll have 3.0. Then we'll bring down another 0 to get 100, and 20 goes into 100 5 times. So I'm not honestly really sure whether you're going to have to bubble in the fractional answer or the decimal answer, but either way, your answer is going to be either 61/20 or 3.05. Number 26 says, what is the area of the region in the first quadrant that is bounded by the line y equals 6x and the parabola y equals 3x squared? So to visualize the problem here, let's sketch out y equals 6x, which is a linear function that crosses through the origin. It's got a y-intercept of 0. This sketch is not going to be to scale, but hopefully it helps you visualize how we'll approach this problem. Also, we've got a parabola 3x squared. Because we're only looking at the first quadrant, I'm only going to put this piece of the parabola in there. There's going to be another side over to the left. And again, this is not really supposed to be a super accurate sketch. It's just trying to give you an idea of what region we're actually trying to find the area of, which is going to be this region up in here. The strategy we're going to use here is we are going to integrate both of these functions and then find the difference between them. When you find a definite integral, you are trying to find the area underneath that curve in between the boundaries you select. Now here, one thing that we don't know yet is what the right-hand boundary needs to be. I'm just going to call that A for now. We don't know where these two curves intersect, although we will find them momentarily. The initial boundary right here is 0. So let's take a minute before we get into any of the calculus and just do a little algebra to find out where those two curves intersect. We need to know for what x value is 3x squared equal to 6x. And to solve this, we need to set the equation equal to 0, just like how you would solve any quadratic equation. Next, we can factor out 3x as the greatest common factor, leaving me with x minus 2. Now that we've got the expression factored out, we can use the zero product property and set each one of these two factors equal to 0 to find what the x values are, where these two functions intersect. One point, which we already should have assumed is 0, x equals 0, and the other one is at 2. So we know that this right-hand boundary is at 2. We're going to set up an integral from 0 to 2, and we're going to find the difference between that top function, which is 6x, and the bottom function, which is 3x squared. To evaluate this integral, we are going to use the fundamental theorem of calculus, and to do that, we need to first find the antiderivatives of each one of these. We can do that using the power rule, or the anti-power rule. The antiderivative of 6x is 3x squared, and the antiderivative of 3x squared is x cubed. And of course, we need that plus c. We are going to evaluate this from 0 to 2, meaning we are going to substitute in 2 into this expression and substitute in 0, and then find the difference between those two expressions. So first, we'll substitute in 2. 3 times 2 squared minus 2 cubed plus c. And then substituting in 0, we get 3 times 0 squared minus 0 cubed plus c. And when we go to simplify this, hopefully you notice a lot of things are going to cancel out and kind of go away. First things first, and this is going to happen every time you use the fundamental theorem of calculus to evaluate a definite integral. The two constants will cancel out. You have c minus c, which would be 0. And then we have all these other terms over to the right that all equal 0, so we can ignore all of those. And so now we have 3 times 2 squared, 3 times 4, minus 2 cubed, which is 8. 3 times 4 is 12. 12 minus 8 is 4. So the area of the region bounded by those two curves in the first quadrant is 4 square units. This is not a multiple choice question, so you will either need to type or bubble in this answer on your own. Number 27 says, let f be a differentiable function defined on the closed interval from a to b, and let c be a point on the open interval a to b such that, and then we have 3 conditions. The first condition says that the derivative of f at x equals c is 0, meaning you have a horizontal line that's tangent to the graph of f at x equals c. The second condition says that the derivative of f is greater than 0, meaning it's positive between a and c. And then finally, the third condition says that the derivative of f is less than 0, meaning it's negative between c and b. Which of the following statements must be true? To answer this question, we need to analyze all 3 of the conditions that are given. The first one says that the derivative of f at c is 0. So before we go any further, what we need to do is be able to visualize what's happening with the graph of f. So first, I'm going to draw a number line to represent not necessarily the x-axis, but different values that x will take on here. So we're only interested in this interval between a and b, and we know there's some point c that's in between. The first condition says that the slope, or the derivative of f at c, is 0. So we don't really know exactly what's happening with this graph yet, but we know there's a point where x is equal to c, where the tangent line is horizontal because the derivative is 0. This typically happens at a local maximum or local minimum, but it may also happen on a point where we have something like this happening. So let's look at the second 2 conditions and see if we can't narrow down exactly what's happening at c. The second condition says that the derivative of f is positive between a and c. So that means the slope of the graph of f must be positive. So the slope is positive, meaning that f must be increasing from a to c. Then it also says that the derivative of f is negative between c and b, meaning that f must be decreasing from c to b. Whenever f, or any function, changes from increasing to decreasing, that indicates that we have a local maximum at that point where the sign changes. So from a to c, the derivative is positive. At c, the derivative equals 0. And then finally, from c to b, the derivative is negative. Let's look through each of the answer choices to see if we can determine which one is true. Part A says f of c is 0. Without any further information, we cannot determine the value of the function. So A is not going to be true necessarily. It might be true. It might be that the x-axis is actually right here, but we don't have any information to justify that. Choice B says that the second derivative of f at c is 0, but we see that at 0, the function is concave down, which indicates that the second derivative is negative. So it can't be B. If the second derivative was positive, the graph would be concave up, but in this case, the graph is concave down. Letter C says f of c is an absolute maximum value of f on the interval a to b. This must be true because function f is increasing between a and c, decreasing between c and b. So even if we include the endpoints, f of c must be the highest point on the entire graph. Just to look at the other two answer choices to make sure that those are not correct. D says that f of c is an absolute minimum value of f, which you can plainly see cannot be true. And finally, E says the graph of f has a point of inflection at x equals c. A point of inflection is where the concavity changes, and we can see that the concavity definitely does not change at c. So the correct answer to 27 is C. Number 28 says the function f is continuous on the open interval negative pi to pi if f of x equals cosine x minus 1 divided by the product of x and sine x. For x not 0, what is the value of f of 0? The key term here to notice is the fact that f is continuous. And if f is continuous, that means the value of f at 0 is going to equal the limit as x approaches 0 of f of x. So what we really need to do to evaluate f of 0 is to find the limit as x approaches 0. To do that, we'll have to be a little creative about how we algebraically approach this. So I'm going to take the expression cosine x minus 1 over x times sine x and multiply both the numerator and the denominator by sine x. It might not be immediately obvious why I'm doing this, but I think as we go through the problem, it'll become more and more obvious. So with the numerator, I have sine x times cosine x minus 1, and in the denominator, I have x times sine squared x. Now, sine squared x is the same thing, and here you have to know your Pythagorean identities. Sine squared x is the same thing as 1 minus cosine squared x. Now, when you use that Pythagorean identity, you might notice that 1 minus cosine squared x is actually a difference of two squares. So with a difference of two squares, if you have a squared minus b squared, you can factor that out and rewrite that as a plus b times a minus b. So we can rewrite that denominator as x times 1 plus cosine x times 1 minus cosine x. From here, you can see that we almost get the cosine minus 1 to reduce to 1, but not exactly. You see, cosine x minus 1 and 1 minus cosine x are opposites, so they don't cancel out right away. But if we were to factor out a negative 1 out of the cosine x minus 1, then we would have sine x times negative 1 times 1 minus cosine x, which is really what we want so that we can get that 1 minus cosine x to cancel. Here, now we can see that the 1 minus cosine x's are going to reduce to 1. From here, we have two factors in the numerator. We have a sine x and a negative 1, and we have two factors in the denominator, x and 1 plus cosine x. So we can split these two factors up and create a product of two fractions, sine x over x and negative 1 over 1 plus cosine x. Now let's go back to the original statement we made about the continuity of this function, where f of 0 is equal to the limit as x approaches 0. So really what we want here is the limit as x approaches 0 of sine x over x times negative 1 over 1 plus cosine x. When we're finding a limit, we can find the limit of these two factors separately. So I'm actually going to rewrite this last statement a little bit and say limit as x approaches 0 of sine x over x times the limit as x approaches 0 of negative 1 over 1 plus cosine x. So we can find these limits separately. I think it's a little bit easier to do that one over to the right, okay, to do this one, because I can just use direct substitution. Since cosine of 0 is 1, we get negative 1 over 1 plus 1, so that's going to be negative 1/2. And then the limit as x approaches 0 of sine x over x, this might be a limit that you just have memorized. It is going to be 1, but if you forget how to do this limit, we can actually use L'Hopital's rule, which says that when we find a limit and it's indeterminate using direct substitution, we can take the derivative of both the numerator and the denominator and then try direct substitution. So over here, I'm going to do a little bit of scratch work. The limit as x approaches 0 of sine x over x by L'Hopital's rule should equal the limit as x approaches 0 of the derivative of sine x, which is cosine x, over the derivative of x, which is 1. And now I can use direct substitution. If I substitute in 0, I get 1 over 1, which is 1. So this checks out. And finally, we just need to multiply these two fractions. 1 times negative 1/2 is negative 1/2. And so our answer is B. Number 29 says for some constant c, the line y equals 4x plus c is tangent to the graph of the function f of x equals x squared plus 2. What is the value of c? To understand what this question is asking, let's try to visualize what the graph looks like. The function x squared plus 2 is the parent quadratic function, which looks like a parabola, but shifted up 2 units. So this y-intercept here is 2. Then we're looking for a graph of a linear equation where the slope is 4 that intersects with this parabola at some point where they have the same slope. In order for this 4x plus c to be tangent to this graph, that means they do need to intersect at one point. But not only do they need a point that they both pass through, but at that point, they need to have the same slope. So there's really two key pieces of information. One is that they need to intersect. And in order for them to intersect, we need there to be a point that satisfies both y equals 4x plus c and y equals x squared plus 2. Additionally, we do need them to have the same slope, which means that the slope of 4x plus c, which is 4, needs to equal the slope of x squared plus 2, which is 2x. To find each of those slopes, I simply found the derivatives of each of those two functions. In order for these two curves to intersect, we need to set them equal to each other to figure out exactly where that's happening. We are not going to be able to solve this equation because of that c. So what we need is an x value where we can guarantee that the lines will intersect. That's going to come from solving this equation where we have the two slopes set equal to each other. Since 4 equals 2x, x must be 2, which means that the tangent line is going to intersect the parabola where x is 2. So at x equals 2, we've got this line that has a slope of 4, and what we're trying to figure out is the c value on the equation of that line. In other words, where is the y-intercept? So we can solve for that y-intercept algebraically. Now that we know the x-coordinate where the two curves are intersecting, we can substitute that in for x. So 4 times 2 plus c equals 2 squared plus 2. And now we can solve for c. 4 times 2 is 8. 2 squared is 4. 4 plus 2 is 6. And 6 minus 8 is negative 2. So this y-intercept is negative 2. This question is not a multiple choice question, so you will have to fill in this answer manually, but there's your answer, negative 2. Number 30 says the area of the region in the first quadrant between the graph of y equals x times the square root of 4 minus x squared and the x-axis is, and then we have our 5 answer choices. To find the area bounded by this curve and the x-axis, we need to find the integral of that function between a and b, where a and b are the points where the curve intersects with the x-axis. So to find the two x-intercepts, we need to find where does this equation equal 0. We can use the zero product property, since this function is already in factored form, to set each factor equal to 0 and solve them individually. X equals 0 is already solved, so we've got that x-intercept. But to get the other one, we need to square both sides of this equation, then subtract 4 from both sides of the equation, divide both sides by -1, and then finally take the square root, and we get x equals plus or minus 2. So this function is a total of 3 x-intercepts, but we only care about the ones that are in the first quadrant. So we're really only going to concern ourselves with x equals 0 and x equals 2. We don't know exactly what this function looks like, and you're not really expected to know what it looks like. So I'm just going to draw some sort of weird curve. We don't know what that curve looks like, but we're just trying to find the area underneath it. So now that we know the boundaries, we can change that a to b to be from 0 to 2. So we're looking for the integral from 0 to 2 of x times 4 minus x squared dx. This integral is going to be solved using u-substitution. So that means that we are going to substitute an expression in this equation with something where we can find a modified version of the derivative also in the expression. So we're going to use u-substitution and select u to be 4 minus x squared. Now we don't have the derivative of that directly in the equation. Du would be negative 2x dx, but in our expression we only have x dx, so we need to rearrange this du equation by dividing both sides by -2, and we get -1/2 du equals x dx, which we actually do have in that expression. So now let's go ahead and make our u substitution, replacing 4 minus x squared with u, and replacing x dx with -1/2 du. So this is going to be the integral from not 0 to 2 anymore. We can find the new boundaries under this u substitution by plugging in 0 and 2 into our u equation. So 4 minus 0 squared would be 4, and 4 minus 2 squared would be 0. So we have this new integral from 4 to 0 of -1/2 square root of u du. Next, I'm going to factor out the -1/2 here and also switch the boundaries here. Notice 4 is actually greater than 0. So to make this a little simpler, I'm going to swap those out so that it's going from 0 to 4 instead of from 4 to 0. To do that, I need to negate the entire integral. So I'm going to actually do these two steps at once. I'm going to swap those two boundaries and negate the integral, and also factor out a -1/2. So I'll have -1/2. The negative will just cancel out and become positive. So I have 1/2, and then the integral from 0 to 4 of the square root of u, which can also be written as u to the 1/2 power. Next, to integrate this, we need to find the antiderivative of u to the 1/2 power, and we can just use the anti-power rule to find that. So here I've got 1/2 times the antiderivative of u to the 1/2 would be u to the 3/2, add 1 to the exponent, and then divide by that new exponent. Dividing by 3/2 would be equivalent to multiplying by 2/3, and then we have a plus c. And we want to evaluate that from 0 to 4 using the fundamental theorem of calculus to come up with our answer. Now, one nice thing about the u-substitution method is that you don't necessarily need to go back and replace everything that's in terms of u with expressions in terms of x. We can simply find the value with the new u expression. So I'm going to take this work, kind of push it over to the side here, and now I'll substitute in 4 and 0 into u and then subtract those two expressions. So here we go. We've got equals 1/2 times 2/3 times 4 to the 3/2 plus c minus 1/2 times 2/3 times 0 to the 3/2 plus c. Now, the plus c's we can more or less ignore because they will cancel each other out. Half of a c minus another half of a c, that sum will be 0, so we can ignore the plus c's. We can also, see that this second term, 0 to any power, is just going to be 0. So this whole thing's going to be 0. Multiplying by 1/2 is also going to be 0. So this whole expression over here to the right is just 0. So let's focus in on what we've got going on to the left. We have 1/2 times 2/3 times 4 to the 3/2 power, which is the square root of 4 to the 3rd power. So 1/2 times 2/3 times the square root of 4 is 2. 2 cubed is 8. And now we're ready to multiply all those together. We have 1 times 2 times 8, which is 16. 2 times 3, which is 6. This can be reduced. If we divide both the numerator and the denominator by 2, we get 8/3, which is our answer. That is the area under the curve bounded by x times square root of 4 minus x squared and the x-axis. Our answer is B. Number 31 wants us to evaluate the definite integral from 0 to 6 of the absolute value of x squared minus 6x plus 8. The number one thing to remember about absolute value functions is that they're actually just piecewise functions in disguise. For example, if we take the parent absolute value function, the absolute value of x, what this function does is output the positive version of any number that you input. In other words, if x is positive, nothing happens. And this is true for 0 also. So as long as the number is not negative, the output will be whatever you input. However, if the value that you're inputting is negative, then the function is going to flip the value and make that the opposite of what you inputted. For example, the absolute value of 5 is 5, and the absolute value of -5 is also positive 5. One way to think about it is that it's the distance away from 0. So -5 and 5 are both 5 units away from 0, which is why they both have the same absolute value. If we think about the graph of this absolute value of x, one way to consider it is to consider just simply y equals x, which is your parent linear function, and you should know that it looks something like this. However, if we do y equals the absolute value of x, then all of the negative outputs will switch to being positive outputs. So instead of all this negative stuff down here, we still have all the positive values on the right-hand side, but instead of all these negative values, these get flipped up into the second quadrant up here, and the graph of y equals absolute value of x just looks like this. Now, the reason why I'm bringing up all this piecewise function stuff is because what we really need to do is to split up this integral into the different pieces. So if we wanted to say find an integral of the absolute value of x, we would find the integral from whatever, let's say we're going from -2 to 2, we'd go from -2 to 0 to find this area, and then add that to an integral of going from, let's say, 0 to 2. So we'd basically have to split this up into 2 separate sections to be able to find that integral. So now let's look at the one that we're actually trying to solve for, which is the absolute value of x squared minus 6x plus 8. To know exactly where the sign is changing here so that we know which parts of the graph need to be flipped up to be positive, we need to find the x-intercepts of that function. Now we're looking at y equals the absolute value of x squared minus 6x plus 8. Let's think about what that graph might look like. It is going to be a piecewise function, but let's pretend that it's not. In other words, let's consider the graph of y equals just simply x squared minus 6x plus 8. Let's find the x-intercepts to make graphing this parabola a little easier. To find the x-intercepts, we need to set the equation equal to 0 and then factor x squared minus 6x plus 8 to get x minus 4 times x minus 2. If we use the zero product property and set each of these equal to 0, we're going to get x equals 4 and x equals 2. These 2 points are the x-intercepts of x squared minus 6x plus 8. So if we want to imagine what this graph looks like, it has an x-intercept at 2, an x-intercept at 4, and since the leading coefficient is positive, we know this is an upward-facing parabola. In other words, it's concave up, the second derivative is positive, and the graph looks like this. Now, what we're more concerned about, though, is the absolute value of x squared minus 6x plus 8. And just like with the absolute value of x, the absolute value of this quadratic is simply going to take all of the negative outputs and flip them up to be positive. In other words, this graph is going to look more like this. It's going to look exactly like the graph we just drew. It's going to have x-intercepts at 2 and 4. And the parabola is pretty much going to look the same, except we're not going to have any of those negative outputs. Instead, these are going to be flipped, and your graph is going to look something like this. So now that we have a better idea of what this looks like, we can set up our integral appropriately. This is going to take a little bit of work, so hopefully you don't mind. At this point, I'm going to erase everything that's not relevant, and I'll move this up here. And now we can start to set up our integral. We want to go from 0 to 6. So 6 is going to be somewhere out here. I'll just plot a point here. And then we do want to go to 0, so I'll just make this kind of connect to where 0 is. I'm not drawing this to scale or anything. We can split this up and find the integral from 0 to 2. So in other words, find this area, and then add that to the area that we find between 2 and 4. And then again, find the integral between 4 and 6. And we can actually take advantage of the fact that a parabola is symmetrical here. So whatever we get for the area between 0 and 2 should be the same as the area between 4 and 6. So let's go ahead and kind of write all this out. First, we'll start with that green area, which will be the integral from 0 to 2 of x squared minus 6x plus 8 dx, and then plus that middle section, so plus the integral from 2 to 4 of x squared minus 6x plus 8. Now hold on here. That middle section was the flipped section. Do you remember that? So we actually don't want x squared minus 6x plus 8. We actually want the opposite of that. So instead of adding that area, I'm going to add the opposite of that area. So I'm going to change that plus to a minus. Okay. The last section here is going to be the same value as the first section. I'm going to write plus, and then I will write from 4 to 6, but I just want you to make a mental note that this is going to have the same value as that first section. And let's squeeze in a little dx here. All right, now we're ready to start evaluating, and we can use the fundamental theorem of calculus to find the value of all these definite integrals. The basic idea here is that we are going to use the anti-power rule to find the antiderivative of this expression here. Now, it's the same expression in all of these, so we only really need to find it once. So let's go ahead and find that. We'll use the anti-power rule to get 1/3 x cubed minus 3x squared plus 8x. And we're going to evaluate that from 0 to 2. Next, we're going to subtract whatever we get here, which will be the same antiderivative, but here we're going to evaluate from 2 to 4. Last, we're going to have this other integral, and this is getting a little out of hand, but just remember, this last one's going to have the same area as the first one, so we won't really have to compute this separately. Okay, so the next few steps is where it gets a little, I wouldn't say tricky, but you really have to be paying close attention to all the numbers we'll be plugging in because there's a lot of fractions involved. So let's start by evaluating that first integral. We will plug in 2 and we'll plug in 0 and subtract those two values. Plugging in 2 is going to give me 1/3 times 2 cubed minus 3 times 2 squared plus 8 times 2. Now we will have to subtract what we get when we plug 0 into this, but notice each term has an x. So if I plug in 0 to all these, they will all 0 out. So we'll be subtracting 0 effectively. I'm not going to write that out. Now for the next piece, we have minus, and here we're going to subtract this integral. So we want to be careful because we're actually subtracting the difference between what we get when we plug in 4 and what we get when we plug in 2. So I'm actually going to put like brackets on here to remember that we're subtracting both of those. So let's go ahead and plug in 4. So 1/3 times 4 cubed minus 3 times 4 squared plus 8 times 4. All of that minus what we get when we plug in 2, which we already did over here, so just keep that in mind. 1/3 times 2 cubed minus 3 times 2 squared plus 8 times 2. Now for this last one, I'm actually just going to kind of hesitate to put anything in here because you can see, like, if I try to plug in 6 and 4, especially without a calculator, these two expressions are going to be pretty hard to evaluate without a calculator. You know, trying to plug in like 6 cubed and 4 cubed, like the numbers are just kind of getting out of hand. But if we notice the symmetry that exists on the parabola, we have this line of symmetry right down the middle. We can see that both of those two sections that I've highlighted in green are equal. So I'm just going to leave this blank for now and just know that it's going to equal whatever I get here. Okay, so let's simplify a little bit more. We've got 2 cubed, which is 8. 8 divided by 3, so 8/3. Minus 2 squared is 4 times 3 is 12 plus 16. And whatever we get there, remember, is also going to go here. Minus, and here, since I'm subtracting this whole thing, I'm going to just like sort of distribute this minus and subtract both of these. So I'll have minus 1/3 times 4 cubed. That's 4 times 4, which is 16 times 4 is 64. Minus 4 squared is 16. 16 times 3, I might have to do a little scratch work out here, but 16 times 3 is going to be 48. And then plus 8 times 4, which is 32. Next, I'm subtracting the opposite of this next expression, so I'm actually adding it. So plus, and notice that I have the exact same thing that I had over to the left, so I'm not really going to think too hard about this. I am simply going to just copy what I have over there. So 8/3 minus 12 plus 16, and then plus whatever we get for that first piece. So just as a reminder, whatever we get over here is going to be the same. And once again, that's because we've got this line of symmetry going right down the middle of that parabola. So that all the area on the left side will equal everything on the right side. Okay, so let's go ahead and start just doing some computations here. This is where it just gets, you can really eat up a lot of time here. Honestly, this question's taken way longer than you really have. And this may be one where you just, if you can't do the arithmetic fast enough, you might just skip it and maybe come back to it at the end of the test. But let's just try to knock it out here. So that first section, we've got 8/3 minus 12 plus 16. Well, 16 minus 12 is 4. And if we're going to write 4 in terms of thirds, 4 is 12/3. So we've got 8/3 plus 12/3, which is going to be a total of 20/3. So we've got 20/3. And now that 20/3, now that we've identified what that area is on the left-hand side, we know this is going to be 20/3 on the right-hand side as well. So we can just kind of fill that in at this point. So 20/3, and now we need to evaluate these other two expressions. Notice over here we get another 20/3, that 8/3 minus 12 plus 16, so don't waste your time trying to do that. But that middle piece we are going to have to crank through. So I'm just going to write some scratch work over here. 64/3 is going to be that first term, and then we've got 32 minus 48. And what I like to do when I have subtraction where I'm subtracting a bigger number from a smaller number is just think of the reverse operation there. Okay, 48 minus 32, 16. And so that means negative 48 plus 32 would be a negative 16. So we've got 64/3
minus 16. Now we need to think about how many thirds that is. So 64 over 3 minus, we already did the math over here, 16 times 3 is 48, so 48 thirds. And 64 minus 48 is 16, so we get 16 thirds. So minus, after all that, minus 16 thirds. And then now we've got that extra plus 20 thirds from right here. It's just the same computation we had before. And then we have one more plus 20 thirds. So we have 20 thirds plus 20 thirds plus 20 thirds. That's 60 thirds minus 16 thirds is a total of 44 thirds. And that is going to be our answer for this problem, which is choice C. Number 32 says a particle moves along the x-axis, and its velocity at time t is given by the velocity function v of t, which is equal to t cubed minus 3t squared plus 12t plus 8. What is the maximum acceleration of the particle on the interval 0 to 3? To find an absolute maximum value on a function on a closed interval, we need to use the candidates test. And essentially what that means is we are going to construct a table of values for different t values and find the acceleration at those t values. Specifically, we're going to be interested in the endpoints of the interval, so 0 and 3, and then any other critical values that the acceleration function has. So notice in the problem that the acceleration function isn't actually given, so you have to find it. And the relationship that you need to know for this problem is that acceleration is the derivative of velocity. So if the velocity function, which is given, is t cubed minus 3t squared plus 12t plus 8, we can use the power rule to differentiate each term there and get our acceleration function, which would be 3t squared minus 6t plus 12. To find critical values of a function, and these critical values are going to be entered into our candidates test, we need to find when the slope is 0. So we actually have to find the derivative of acceleration, which we're not going to really have a name for. We're just going to call it the derivative of acceleration. And we can use the power rule once again and get the derivative of acceleration, which is 6t minus 6. The critical values of any function are those x values, or in this case, t values, that make the derivative of acceleration either equal 0 or undefined. 6t minus 6 is never going to be undefined because it is a linear function, and all polynomial functions are continuous from negative infinity to infinity. In other words, it will never be undefined, but it will equal 0 for one t value. So let's find out what that t value is. 6t minus 6 equals 0 means that 6t equals 6, and then t equals 1. So this t equals 1 represents either a local maximum, a local minimum, potentially neither. The candidates test says that if you're looking for an absolute maximum or an absolute minimum, that value will occur either at the endpoints of a closed interval or at a critical value. So now that we've identified the endpoints of the interval, which are 0 and 3, given right here, and we've identified all the critical values, and there's just one, it's 1, we can now perform the candidates test to find the absolute maximum of the acceleration function on that closed interval. All we need to do is just substitute these values into our acceleration function, which is right here. If I substitute in 0, I'm going to get 3 times 0 squared minus 6 times 0 plus 12, which is just going to equal 0 minus 0 plus 12, which is 12. If I substitute in 1, I get 3 times 1 squared minus 6 times 1 plus 12, which would be 3 minus 6, which is negative 3, plus 12 is 9. And finally, at t equals 3, the acceleration would be 3 squared is 9 times 3 is 27. Maybe it's worth doing a little scratch work here so I don't mess up the arithmetic. 27 minus 18 plus 12 27 and 12 make 39. 39 minus 18 is 21. And so the absolute maximum acceleration value is going to be the largest output on this table. And we can see that that is 21. That's going to be our answer, which is answer choice D. Number 33 says the graph of f prime, the derivative of the continuous function f, is shown in the figure above. Which of the following statements must be false? And to answer this question, we have to analyze that graph pretty carefully and understand what information is implied about f given this graph of f prime. So before we start thinking about what must be happening about f, let's recall that f prime is the derivative of f, meaning that f prime describes the slope of f. So what I'd like to do is take this graph of f prime and really just kind of look at it piece by piece. I'm not going to try to analyze everything that's going on here all at once, but rather look at individual sections. So the first thing I'm looking at is going from left to right, this section right here. Notice that f prime is completely above the x-axis on this section, meaning that f prime is positive on that section. Not only is f prime positive here, but it's also increasing, it's going up. So that means that the slope of f must be increasing and positive in this section. Now, if we look at the next section, and I'll just, for right now, look between -2 and 0, notice that the graph of f prime is still above the x-axis. But the difference between this section and the first section is that now f prime is decreasing. So if we think about what's happening with f between -∞ and -2, although we don't know exactly where the graph would be positioned vertically, we know that the slope of the graph is going to be positive, meaning f is increasing, up to a point where we have a vertical tangent line. A vertical tangent line implies that the slope is undefined there, and that's why we have an asymptote on f prime. Now, after -2 and all the way to 0, we still have a positive slope, but the slope is decreasing all the way to 0, which means the graph of f, while it's still going up, is kind of curving downwards and getting closer and closer to being horizontal. Whenever f has a horizontal tangent line, that means that f prime is 0. So this point right here on f prime is going to correspond to a point on f where we've got a horizontal tangent line. Now after 0, and specifically between 0 and 2, we see that f prime is negative, meaning that f should be decreasing on that interval. And it's decreasing all the way down to -∞, which means we are going to have another vertical tangent line. So the slope is going to be going downward. And then at 2, we have a vertical tangent line. And after 2, we see that although f prime is still negative, it is now increasing towards 0. So that means that the graph of f is going to be trending towards having another horizontal asymptote. So f is going to more or less look something like this. So now let's go through all the answer choices and see if we can find a false statement. A says that f has no relative extrema. Now on f, we can clearly see that we do have a relative maximum. So this is going to be false. This is going to be our answer. But just to be sure, let's go through B, C, D, and E, the rest of these answer choices, to make sure that it's the only one that must be false. Another reason why we know this has to be false, because at x equals 0, f prime is going from being positive to negative, and this is what indicates a relative maximum. Choice B says that f is increasing on the interval -∞ to 0. Well, in order for f to be increasing, that means that f prime must be positive. And that is true. On the interval -∞ to 0, we can see that the graph of f prime is completely above the x-axis. So that has to be true, meaning that's definitely not going to be our answer. Choice C says the graph of f is concave down on the interval -2 to 2. Now, in order for the graph of f to be concave down, not only does f double prime, or the second derivative, need to be negative, but also f prime must be decreasing. In other words, it has a negative slope. So look back at that graph at f prime. From -2 to 2, which would be this portion right here, you can see that on that entire interval, f prime is decreasing. It has a negative slope. So this statement must be true, which means it's not going to be our answer. Choice D says the graph of f has points of inflection at -2 and 2. A point of inflection indicates that f double prime changes sign. We have a sign change on the second derivative. This also implies that the slope of f prime changes sign. And we can see from the graph, and this would be a good point to erase all that extra highlighting, to see that at -2, the slope is changing sign. The slope changes from being positive to negative. And at +2, the slope of f prime changes from negative to positive. We have a sign change in the slope of f prime, which means that there is a sign change of f double prime, which indicates that f has a point of inflection at both -2 and 2. That means that this statement's true, so that's not going to be our answer. Finally, E says the graph of f has vertical tangent lines at -2 and 2. And this is also going to be true because we have those vertical asymptotes at -2 and 2, indicating that we have vertical tangent lines on f. So for sure, our answer is A. We were already pretty sure of that after reading it to begin with, but going through the rest of the answer choices is helpful to increase our confidence that we got the question right. Number 34 says if f is a continuous even function such that the integral from 0 to 3 of f of x dx is -4, then what is the integral from -3 to 3 of 5 f of x plus 1 dx? The key piece of information that you need to understand about this problem is that f is an even function. An even function means that f of -x equals f of x. This is simply the definition of an even function, but what is going to be helpful in solving this equation is understanding how this property plays out graphically. Basically, if a function is even, it is symmetrical across the y-axis, meaning that the graph between -3 and 0 will be the mirror image of the graph between 0 and 3. The next thing to understand is that definite integrals are accumulation functions, meaning we're finding the area between the lower and upper bounds of the integral. So we don't really know what f of x looks like, but when it says that the integral from 0 to 3 on this function is -4, let's say 0 is here and 3 is over here. If the integral is -4, that means that the area is below the x-axis and the total area underneath there is 4. In other words, we have an area, we don't know what f of x looks like. I'm just drawing a little hump here to kind of give you an idea of what it might look like. But the important part here is that the area here, which is a signed area, is -4. All the area that we calculate below the x-axis, we calculate as negative area. Now, again, we don't know what the graph looks like. Maybe it looks like that. Maybe it does something like this. But regardless of what it looks like, that area is definitely 4. Now, because the function is even, that means that whatever the function looks like on the right-hand side of the y-axis, we have a mirror image on the left side of the y-axis. It should look exactly the same, meaning between -3 and 0, we should have the exact same area. This is really the key to solving this problem.
So now let's go ahead and try to calculate the definite integral it's asking for. We want the integral from -3 to 3 of 5 f of x plus 1 dx. Since the function f is even, then we can actually rewrite this as 2 times the area between 0 and 3. From here, we can just use our properties of integration to split this up and make this a little bit easier to solve. So first, I'm going to split up these terms. Since we have a sum here, we can split up the integral and say that this is going to be 2 times the integral from 0 to 3 of 5 times f of x dx plus 2 times the integral from 0 to 3 of 1 dx. We can also factor out the 5 in that first integral and say 2 times 5 is 10, so we can rewrite it like this. The integral from 0 to 3 of the function 1 is just 3. If you're having trouble understanding why that would be 3, try to envision the graph of y equals 1, which would just be a horizontal line at y equals 1. And if you're calculating the area between 0 and 3, that's just going to be the area of a rectangle with dimensions 1 and 3. So 1 times 3 is 3. Generally speaking, if you have a constant function that you're trying to find the definite integral of, you can simply multiply that number by the difference of the upper and lower bounds. Now to simplify this a little bit more, we can evaluate the integral from 0 to 3 of f of x dx because that was given in the original problem. We know that's -4. So we have 10 times -4 plus 2 times 3 is 6. This is going to give us -40 plus 6, which equals -34. So our answer is B. Number 35 says the graph of the function f, shown in the figure above, has a vertical tangent at x equals 1 and a horizontal tangent at x equals 2. For each of the following values of x, indicate whether f is not continuous, continuous but not differentiable, or differentiable. So there's two key words here, continuous and differentiable. It's important to know that if a function is differentiable, it is automatically continuous. Differentiability implies continuity. The contrapositive of that statement is that if a function is not continuous, then it is not differentiable. When you're looking at a graph, you can tell if a function is continuous at a point if you could sketch that graph without lifting your pencil. So there is one point on here where the function is not continuous, and that is at x equals 0. We could see that if we try to draw this function, we'd have to lift our pencil to draw this other point and then continue on with the graph. We can't draw the graph at x equals 0 without lifting our pencil. Now the rest of the graph is fine. You can see that you could draw this without lifting your pencil. So that's the only point where f is not continuous. To determine if a function is differentiable at a point, you want to be looking for certain characteristics of that graph. A function is not differentiable if it contains any of the following: a cusp or a corner, or sometimes it's called a sharp turn in the graph, indicates that the limits of the slope of the graph are not equal on the left and the right-hand side. The most common function to see a cusp in is going to be your absolute value function. Basically, anytime you've got that sharp turn, the function's not going to be differentiable. And we see a sharp turn occurring at x equals 3. So the function is not differentiable there. Also, a function will not be differentiable if there is a vertical tangent line. In other words, if your graph is doing something like this, and we see we have a vertical tangent, even though it's continuous, it is not differentiable there. The last case that we want to be on the lookout for is any place where we have a discontinuity. And that is because if a function is not continuous, it is not differentiable. This could be a removable discontinuity like a hole in the graph, or it might be a non-removable discontinuity, like if you have a jump, something like this, or a vertical asymptote. So if your function's doing something like this with a vertical asymptote. So let's look back at that graph. We already discussed that we have a discontinuity here, so it's not continuous here. But there are two other locations where the function is not differentiable. It's not going to be differentiable when you have a vertical tangent line, and it's not going to be differentiable when you have a cusp. So at both of these locations, f of x is not differentiable. So now let's look at that table and see if we can put some check marks in the correct boxes. At x equals 0, the function is not continuous at x. At x equals 0, the function is not continuous at x because of that removable discontinuity, and if it's not continuous, it can't be differentiable. So we're going to put a check mark here. At x equals 1, right here, we have a vertical tangent line. So while the function is continuous, it is not differentiable. So the check mark needs to go here. At x equals 2, the function is continuous and is differentiable. There's no discontinuity, and there's nothing that prevents you from finding the slope. In fact, we know exactly what the slope is at 2. It's 0. So if you can differentiate, you know that it's differentiable. The check mark for x equals 2 needs to go here. And finally, at x equals 3, we have that cusp. So while the function is continuous, it is not differentiable. So the last check mark needs to go here. Number 36 says, which of the following is a right Riemann sum approximation for the definite integral between 0 and 2 of the square root of x dx using n subintervals of equal width? A Riemann sum is a technique that is used to estimate definite integrals. The function that we are attempting to estimate this integral for is the square root of x. And if we visualize what that graph looks like, it'll be easier to understand how this right Riemann sum is used to estimate the area under the curve. Whenever you have a definite integral, it will equal the area bounded by the curve and the x-axis, with any area underneath the x-axis being negative. So what we're trying to do is estimate this area underneath here. A right Riemann sum is going to require that you draw rectangles in a way so that the right-hand side is equal to the value of the function. So for instance, if we were to split this up into, say, 4 subintervals, I would have partitions at 1/2, 1, 1.5, and 2, and I could draw rectangles that hit this function on the right-hand side. The area that these 4 rectangles take up is an estimate for the area underneath the curve. Obviously, it's not a great estimate because we have all this extra area that we really don't want to include in our integral. So instead of having 4 intervals, what if we had more? If we had 8 intervals, you can see that although it's still a little bit of an overestimate, it's definitely closer to the actual value. Our goal here would be to optimally have infinitely many of these rectangles to give us the best idea of what that area is going to be. So when we calculate a Riemann sum as a way to approximate the area underneath a curve, we basically just find the area of each one of these rectangles and add them up. The way that we find area of a rectangle is just the horizontal dimension multiplied by the vertical dimension, x times y, or base times height, length times width. Once we have the area of all of these rectangles, adding them together will give us our estimate. So this sigma notation that we see on all of these answer choices is really just saying, hey, we're going to add together a bunch of rectangles, starting with the first one and going to the nth one. So there are n rectangles. That's why it says n subintervals. The setup here is going to be to find the sum from 1 to n, meaning starting with the first rectangle and ending with the nth one. And then for each rectangle, we want to multiply the base by the height. The base will be the length of the interval. In other words, all of these intervals should be the same length. I know in this sketch it doesn't really look like that, but whatever this interval length is, that's going to be the length of the base. Since we don't know how many rectangles we actually want here, it's n, so it's an unknown value, we would take the total interval length here, which is 2, and then divide it up by that many rectangles. For instance, if there were 8 rectangles, each one would be 2 divided by 8, or have a width of 1/4. So we'll take that total interval length, which is 2, and divide it by n. Again, the 2 here represents the total interval length. You can calculate that by simply subtracting the 2 bounds. In a right-hand Riemann sum, the height of the rectangle is based on the right-hand partition. And the actual value of the height will be given by the function itself. So for instance, the height of this last rectangle would be the square root of 2. The height of the rectangle at x equals 1 would be the square root of 1, which is 1. So to come up with the height, we're going to input into our square root function the total length of the interval, which was 2, divided by how many rectangles we have, times k, which is the rectangle number. So for instance, on the first rectangle, assuming we have 8 of them, this one right here that I'm pointing at, that height is going to be the square root of 2 divided by 8, that'd be 1/4, times 1, where 1 is the first rectangle. So that would be 1/4. That's pretty much it for this problem. Our answer is E. Number 37 says, let f and g be continuous functions such that the limit as x approaches -4 of f of x equals 3, and the limit as x approaches -4 of g of x equals 1. What is the limit as x approaches -4 of f of x plus g of x squared, all divided by 3 times g of x minus f of x squared? Give your answer as a fraction. This is an open-ended question. There are no multiple choice options, but luckily this problem turns out to be pretty easy once you realize all you have to do is use your limit properties to split this up and evaluate each limit separately. Let's go ahead and do that. The first thing I'm going to do is to rewrite this, but with the limit just totally split up. So each individual piece of this expression is going to have its own limit. So this will be equal to the limit as x approaches -4 of f of x plus the limit as x approaches -4 of g of x, all of that squared, divided by the limit as x approaches -4 of g of x times 3 minus the limit as x approaches -4 of f of x, and that quantity will be squared like in the numerator. Both of these limits are given. The limit as x approaches -4 of f is 3, and the limit as x approaches -4 of g is 1. So we can make those substitutions. That gives me 3 plus 1 squared over 3 times 1 minus 3 squared, which equals 3 plus 1 over 3 minus 9, 4 over -6, which reduces to -2/3. Number 38 doesn't really have any instructions. They're just asking us to evaluate the definite integral from 0 to 2 of x over 1 plus x dx. To get this question right, you need to be able to walk into the test knowing what the integral of 1 over x dx is. This ought to be one of the antiderivatives that you have memorized, and it is the natural log of the absolute value of x plus c. So you just need to know this one in order to get this question right. And if we look at the expression, it kind of looks like that. There's a little bit more going on in the denominator than we'd like, and we have an x in the numerator. But what we can do is we can manipulate this expression a little bit using what's called a u-substitution.
And basically the way this works is we're going to take an expression that we find inside the x over 1 plus x expression and say that that is u. That'll give us du. And then from there, we should be able to kind of rearrange this a little bit to get it to a point to where the anti-differentiation is not as difficult as it looks to begin with. So if we let u be 1 plus x, then that tells me that du is the derivative of 1 plus x, so that's just dx. Now, in the expression, we do have 1 plus x right here. We also have an x here that we'll need to rewrite. If u is 1 plus x, then that means x is u minus 1. So now let's rewrite this integral with those substitutions. So we have the integral. I'll come back to the bounds because those are going to change. X is u minus 1, and x plus 1, or 1 plus x, is u, and dx is du. Now regarding the bounds, the upper and lower bounds, 0 and 2, we will need to adjust those because we are using this u-substitution technique. If u is 1 plus x, then 1 plus 0 is 1, and 1 plus 2 is 3. Essentially, we're taking these x values and converting them into u values, and u is 1 plus x in this case. So now we've got an expression that's going to be a little bit easier to break up. We can rewrite this as u over u, which is going to just be 1, minus the integral from 1 to 3 of 1 over u du. And I forgot a little du in here. So rewriting that one more time, we've got the integral from 1 to 3 of 1 du minus the integral from 1 to 3 of 1 over u du. Now the integral of 1 from 1 to 3 is just going to be 1 times 2, where 2 is the distance between the bounds, 1 and 3. One way to conceptualize why that would be 1 times 2 is to imagine the graph. Y equals 1 is just a horizontal line passing through the point where y is 1. And if we want the integral from 1 to 3, that's just the area underneath that curve, which we can see is a rectangle with dimensions 2 by 1. And so that's why the integral from 1 to 3 of 1 is 1 times 2. In general, if you're trying to integrate a constant, you just multiply that constant by the distance between the upper and lower bounds. So really not too bad. Then we have minus, and this is where we're going to have to be careful here. We need to find the antiderivative of 1 over u and evaluate it from 1 to 3. The antiderivative of 1 over u, as we can see up here, is going to be the natural log of the absolute value of u. So we need to plug in 3, we need to plug in 1, and then we can simplify. This will be 2 minus, and I'm actually going to leave all this in brackets just to make sure that my subtraction works out correctly. The natural log of the absolute value of 3 minus the natural log of the absolute value of 1. Now the absolute value of 3 is just 3, and the absolute value of 1 is just 1, so we can safely drop those absolute value bars and just evaluate each one. Natural log of 3 is irrational, so we're just going to leave it as natural log of 3. And then the natural log of 1 is 0. So we're not going to write anything. It's just going to be plus 0. So there's your answer, and we can see that the correct answer is choice B. Number 39 says, let f be the function defined by -3 over x squared plus 4 over x cubed with a domain of all positive values. What is the minimum value of f on its domain? When you're looking for local minima, which are going to be the lowest points on a graph, and local maxima, which are going to be high points on a graph, we should be looking for where is the slope of that graph equal to 0. In other words, when is the derivative equal to 0? So you will find local extrema, whether it be a maximum or a minimum, wherever the critical values of a function exist. Critical values of a function named f are any x values that make the derivative equal 0. The derivative being 0 typically will indicate that you have a horizontal tangent line, and that's where these local maximum and minima exist. Once we find the x values that make the derivative equal to 0, we can analyze what's happening to the function around that point. And if we notice that the slope goes from being negative to positive, in other words, going down and then coming back up, then we know that that point's going to be a minimum. And if the slope is going from being positive to negative, in other words, going up and then coming back down, we know we have a maximum. Now, we're not really looking for a maximum in this problem. We're more interested in the minimum, but this is a good opportunity to just point out how you would solve a similarly worded problem. So let's first find that derivative, set it equal to 0, and then we can start our analysis. The first thing I'm going to suggest you do is to rewrite this function f of x as a polynomial. Now, it's technically not a polynomial function, but we still want to write it in that polynomial format so that we can take advantage of all of the derivative rules that we know. For instance, here we can use the power rule to find the derivative of f. So our derivative would be 6x to the negative third minus 12x to the negative fourth, which if we want to go back and rewrite it as it was written before, would be 6 over x cubed minus 12 over x to the fourth. So now that we have that derivative, let's set it equal to 0, solve that equation, and then find those critical values. To do that, we can start by multiplying both sides of this equation by x cubed, and that's really going to clean up the equation quite a bit. It gives us 6 minus 12 over x equals 0. We can subtract 6 from both sides to get negative 12 over x equals negative 6. Multiply x on both sides, and then divide both sides by negative 6. And so the only critical value we come across is 2. Now, that is not going to be our minimum value, even if that ends up being a place where we have a minimum. This is simply the x value. When the question is asking for the minimum value, it's actually asking for a value of f. So we're going to have to plug this back into f and find what that minimum value is. But let's take a moment to just verify that we do in fact have a minimum value there rather than a maximum. So one way to test this is to draw a number line, and I'm going to actually just start at 0 here because we have a domain restriction that x must be greater than 0 anyway, and place that critical value that we just found, x equals 2, on the number line, and then choose a representative from each interval that we have here to plug into f prime to find out whether the slope of f is positive or negative. Again, we should be plugging this into f prime. So, for example, if we plug in 1, which would be some number in this interval, we would get 6 over 1 minus 12 over 1, and that is going to be negative. 6 minus 12, we don't really care exactly what it equals, we just know that it's negative. So the slope of f between 0 and 2 is negative. And then after 2, if we pick a number like, say, 10, that would give us 6 over 10 cubed minus 12 over 10 to the fourth, this being 6 over 1,000 and 12 over 10,000. You can see pretty clearly that 12 over 10,000 is going to be a much smaller number than 6 over 1,000. So if we subtract them, we should get a positive value. We don't really care exactly what it equals. We're just looking for whether or not it's positive or negative. So this number line, as a reminder, is referring to f prime. So we know the slope of f starts out negative and then at 2 becomes positive. So we for sure have a local minimum at x equals 2. And the last step here is going to be to actually calculate what the minimum value is. We know it's at 2, but what is the value itself? Let's plug that into f of x. F of 2 is negative 3 over 2 squared plus 4 over 2 cubed. That's going to be negative 3/4 plus 4/8. 4/8 is the same thing as 2/4, so we get negative 1/4. And that is our answer. This is not a multiple choice question, so you will have to input this number manually. It is possible that you might have to write this as a decimal, so negative 1/4 is also equal to negative 0.25. Number 40 says if f is a continuous function such that the definite integral of f of t dt from 0 to 2 equals 6, then what is the definite integral of f of 2t dt from 0 to 1 equal? This looks like a pretty confusing problem at first glance until you realize that you can use a u-substitution to solve it a little bit easier. If we let u be 2t, which we have in this expression here, then du, the derivative of 2t, would be 2 dt. With a u substitution, you would like the derivative of whatever you're declaring to be u to be present in the expression you're working with. However, we don't see the 2 there. We've got the dt, but not the 2. So we need to rewrite this equation and divide both sides by 2 to get 1/2 du equals dt so that we can actually make the substitution. So going back to the integral that we're actually trying to evaluate, we've got the integral of f of 2t dt, but I'm going to write that as f of u since u is 2t, and I'll replace the dt with 1/2 du. Now, because the 1/2 is simply a coefficient, we can actually factor that out of the integral completely and write it out to the side. Notice, though, I have left off the upper and lower bounds of this integral, and that's because we have to convert them too. These two, as written, are t values, but we need to convert them to u values. And since we've declared that u is 2t, then we can find the new boundaries. If 0 was t, then u would be 2 times 0, which is 0. So that bottom bound actually stays the same. But if that t value is 1, 2 times 1 is 2, so that upper bound is 2. Now we have an integral that is set up pretty much exactly like what the given integral information gave us. Right here it says the integral of f of t dt from 0 to 2 is 6. So the integral of f of u du from 0 to 2 must also be 6. So then we have 1/2 times 6, which is 3. So our answer is B. Number 41 says let f be the function defined by 2x cubed minus 27x squared. The slope of the line tangent to the graph of f at x equals 2 equals the slope of the line tangent to the graph of f at x equals k, where k is not 2. What is the value of k? So let's break down exactly what this prompt is saying. It says the slope of the line tangent to the graph of f at x equals 2 equals the slope of the line tangent to the graph of f at x equals k. In other words, the slope at x equals 2 needs to equal the slope at x equals k. The slope of any function is given by its derivative. In other words, the derivative of f of x is the function that defines the slope of f of x. So clearly, we're going to need to know what the derivative of f of x is, and we can use the power rule to find it. F prime, which is the derivative of f, is 6x squared minus 54x. So now let's go back to the equation that the prompt is having us set up. The slope at x equals 2 needs to equal the slope at x equals k. So let's find the slope at x equals 2 first. To find that slope at x equals 2, what we really want is f prime at 2. If we want the slope at x equals k, we want f prime at k. So f prime at 2 will be whatever we get if we substitute 2 into the derivative equation. So f prime at 2 would be 6 times 2 squared minus 54 times 2. 2 squared is 4, and 4 times 6 is 24. 2 times 54 is 108. 24 minus 108 would be negative 84. So the slope at x equals 2 is negative 84. The slope at x equals k would be whatever we get when we plug in k, which doesn't really change anything as far as our equation goes. We're just going to replace all the x's with k. So that would be 6k squared minus 54k. Ultimately, we're trying to find the k value that makes this true, so now all we have to do is solve this equation. We can see that it's quadratic because of the k squared, and when we solve any quadratic, generally speaking, we do want it to be equal to 0. So let me rearrange this equation. 6k squared minus 54k plus 84 equals 0. Now, trying to factor this is going to be, well, quite frankly, pretty annoying. So let's instead, before we start factoring anything, is to divide both sides by whatever the GCF, or the greatest common factor, of that left-hand side is. And we can safely divide everything by 6 here. 6 divided by 6 is 1. 54 divided by 6 is 9. And 84 divided by 6 is 14. So now we have something that's a little bit more friendly for us to factor. If we factor this, we get k minus 7 times k minus 2, which leads us to two potential solutions here, either k equals 7 or k equals 2. Since the prompt said that k could not be 2, we are going to throw away that solution as an extraneous solution, which leads us to our only possible answer here, which is 7. This is another non-multiple choice question, so you will have to input this solution in manually. Number 42 says, let f be the function defined by f of x equals x over sine x. Which of the following statements are true? Indicate all such statements. This is not multiple choice, so we may have to circle multiple items here. It is possible just one of these are true, but it says indicate all such statements that are true. All three of these statements have to do with finding limits of that function, and so we may have to use different techniques depending on which limit it's asking for. A is wanting the limit as x approaches 0. It says the limit as x approaches 0 of f of x is 1. Well, if the function that we're working with is x over sine of x, and we want the limit as x approaches 0 of x over sine x, your first attempt should always be to just try direct substitution. In other words, plug in this number into every instance of x and see what it equals. However, when you try that, you get 0 over sine of 0. Sine of 0 is 0. So we're left with an undefined expression that we can call indeterminate. Whenever we have an indeterminate limit like this, we can use L'Hopital's rule. According to L'Hopital's rule, this limit will be equal to the exact same limit of the derivative of the numerator divided by the derivative of the denominator. The derivative of x is 1, and the derivative of sine x is cosine x. That derivative of sine x, being cosine x, by the way, is just one of those transcendental derivatives that you should have memorized. Now I can use direct substitution and just plug in that 0. 1 over cosine 0 is equal to 1 over 1, because cosine of 0 equals 1. And so this does, in fact, equal 1, meaning A is a true statement. Now, again, this is not a multiple choice question, so we do need to check B and C to see if those are true as well. On the next one, we're finding the limit as x approaches pi over 2 of x over sine x. And just like with the first one, we want to try to use direct substitution. In this case, though, it will work. If I substitute in pi over 2 into x, I get pi over 2 over the sine of pi over 2, which equals 1. So pi over 2 divided by 1 is pi over 2, and yep, B is also a true statement. For C, we get the limit as x approaches pi of x over sine x. We want to try using direct substitution again, but here we get pi over 0. It's not exactly equal to here because you can't equal something that is undefined, but this one is one where we're not going to be able to use L'Hopital's rule. Instead, whenever you have a non-zero over a zero, when you try to use direct substitution on a limit, this almost always is going to indicate that you have a vertical asymptote. And anytime that happens, the limit's either going to equal infinity or negative infinity. We don't need to do any investigation to know whether or not this is going to be infinity or negative infinity, because either way, it's definitely not pi. So C is going to be a false statement, meaning the only correct answers here are A and B.
Starting with number 43, all of the questions from here on out are going to be in the calculator section. A graphing calculator will be available for the questions in this section, although, like you'll see in this particular problem, we won't need a calculator for every question. So I won't have it out unless I need it, but when I need it, I will pull it up and show you exactly how I'm using it. Number 43 says the graph of a function f is given above. What is the limit of x divided by f of x plus 1 as x approaches 2? For limit problems, you always want to start with direct substitution. And basically what this means is you just want to plug in this value that x is approaching into x. And if we end up getting a value out of that, that's going to be our answer. And we can shortcut our way through this problem. But if not, we may need to use another strategy. So if I attempt to plug in 2, I'm going to get 2 over f of 2 plus 1. Now the 1 point on the graph that's given is 2 comma negative 1. And so that means that f of 2 is negative 1. So 2 over negative 1 plus 1 gives us 2 over 0, which is undefined. Oftentimes, when you get an undefined limit, the limit is what we call indeterminate. And this happens anytime you get something like 0 over 0, or infinity over infinity, or maybe negative infinity. And in these cases, we would want to use L'Hopital's rule to find the value of the limit. However, in this problem, we do not get 0 over 0. We have a non-zero over 0. And what this typically indicates is that this function here, this x over f of x plus 1, has what we call a vertical asymptote. In other words, the graph of this function around x equals 2 is either going to be doing something like this, or maybe on either side they're both going down, or it could be a combination, either something like that or something like this. And we don't know for sure, but what we can do is test values near x equals 2 to see what's going on. Now we want to test values that are pretty close to 2, and you don't necessarily need to do all the arithmetic to test these values. We're really just trying to see if the behavior of the function is going up or down. And if we test values really close to 2, we really only need to look at whether or not the value of that function is positive or negative. And if it's positive, we're going to assume that the function's going up on that side. And if it's negative, it's going down. So let me go ahead and erase these two because we don't know exactly what's happening on the left-hand side and what's happening on the right-hand side. So let's test both of these. Let's start with the left side. So we want to pick a value really close to 2 that's on the left side of 2. I'm going to go with 1.99. You can get even closer if you want, but I find that usually picking a number that is just 1/100th off of the number that you're trying to find the limit for is good enough. So let's plug in 1.99 and see whether or not this function will be positive or negative. So if I plug in 1.99 into this function here, I get 1.99 over f of 1.99 plus 1. And so the real question is this thing going to be positive or negative? Because obviously 1.99 is positive, but if I look at the graph, I can at least get a pretty good idea of whether or not the denominator is going to be positive or negative. 1.99 is just to the left of 2. So we're really looking at this x value like right about here, probably even closer to 2 than that. And the output here is just going to be barely above -1. So let's call it like -0.9, or probably, again, even closer. But regardless of our estimate of what that value is, we can clearly see that it's greater than -1. So we can say for sure that f of 1.99 plus 1 is going to be a positive value. And so that's telling me that on the left side of that asymptote, the value of the function is going up. Next, let's take a look at the right side. We'll approach this in basically the same way that we approach the left side. We should pick a number that's really close to 2, but just slightly to the right of it. And so I'm going to pick something just the same distance away, 1/100th away. And so I'll pick 2.01 as my x value of the test. So if I plug in 2.01 into x in both places here, I need to determine whether or not that's going to be positive or negative. Now, 2.01 is going to be just slightly to the right of 2, roughly right here. And it looks like about the same value as f of 1.99. So that tells me that this is also going to be positive. Now, since the function is increasing to infinity on both the left and the right-hand side of x equals 2, that tells me that the limit technically doesn't exist, but in these scenarios where you have the vertical asymptote and the function's approaching either infinity or negative infinity on both the left and the right-hand side, it is acceptable shorthand to say, even though it doesn't exist, that the limit is infinity. Number 44 is another problem in the calculator section where you really don't need a calculator. It says, let f be a continuous function, that's capital F. The graph of lowercase f, the derivative of capital F, is given above. Which of the following statements is false? So we really want to go through each of these statements and decide on whether or not they are true or false. The first thing I want to mention here is that it says that the graph of f, which is what we're looking at, is the derivative of capital F. So that means that the derivative of capital F is little f. And so what we're looking at here is actually a graph of the slopes of big F. So part A says capital F of 2 minus capital F of 0 is greater than 0. And basically that means that that expression is positive. So whenever you see the difference between two antiderivative values, typically that is a hint that we want to be using the fundamental theorem of calculus. There are actually two parts of the fundamental theorem of calculus, but to determine whether or not A is true, we're only going to use the second part. And I'll write it generally here. It is a way of calculating definite integrals. So if we want the integral from A to B of some rate function, all we need to do is find the difference between the antiderivative of that rate function at the upper limit of integration and the lower limit of integration. So there's our fundamental theorem of calculus part 2. And let's go ahead and rewrite this a little bit so that it matches the function that we're given here. So the derivative function that we want to integrate here is actually f of x. So I'm going to replace that. And its antiderivative is the capital F of x. So I'm going to rewrite this to make it match this particular problem. Now, if we want to know if f of 2 minus f of 0 is positive, then we really need to examine the integral of f from 0 to 2, because f of 2 minus f of 0, that's basically what we want to compute here. And so that's going to be the same thing as the integral from 0 to 2 of f of x, which is what we see in the picture. Now, all we care about is whether or not this is going to be positive or negative. And so since another way of identifying the value of a definite integral is finding the area bounded by the curve and the x-axis, we can look in between 0 and 2 here and see that all this area is above the x-axis. Therefore, yeah, that's got to be positive. The only time you're going to get negative area is if you have area that is below the x-axis. So this is true, which means this is not going to be our answer. So let's take a look at choice B. Choice B is probably the trickiest one to get your head around. It says f is defined at x equals 2. Now, if you're just reading that too closely, you might think, oh, that's definitely the right answer, because take a look at 2. This is undefined. However, this is not the graph of capital F. This is the graph of little f. And little f is the slope or the derivative of big F. Now, if we look at these values a little closer, you can see that the value of little f, which is the slope of big F, so this is really just the derivative of big F, we can see that the slope of big F is trending towards positive 1. So we can say that the slope of big F is roughly 1 at that point, or like right before that point. And the slope of f is roughly -1, or at least it looks like it's approaching -1 on the right-hand side of x equals 2. So what must be happening here is that the slope of the graph changes instantly from 1 to -1, and that indicates that we have a cusp or a sharp turn in the graph where we have a slope of 1 that instantly changes to -1. So this is what the graph of f of x probably looks like. These slopes are not to scale or anything, but just to give you an idea of what kind of a graph might have this behavior in its derivative. So since this is definitely true, we're not going to select that one either. C says f is differentiable at x equals 2, and that's big F once again. To be differentiable, the derivative must exist. And we can see at x equals 2, the derivative of capital F, which is little f, that is what we're looking at on this graph. The value of little f, the derivative, is undefined. So we can say right here, f of 2 is undefined. And since f of 2 is undefined, that means big F at 2, the derivative of that is undefined. And if the derivative of big F is undefined, that means big F is not differentiable at x equals 2. So this one is false. That is likely going to be our answer, but let's make sure and go through the other answer choices. D says big F has a relative maximum at x equals 2. And we can say that that is true also. This kind of goes back to our discussion when we were going over part B, where what must be happening for function big F is we have this cusp or this sharp turn, and that would represent a relative maximum on the graph there. So D is not going to be our answer either. And finally, E says F is decreasing from 2 to infinity. And in order for F to be decreasing on that interval, the derivative of big F must be negative. And we can see on the graph, the derivative of big F, which is little f, is negative. This whole segment from 2 all the way to infinity is negative. So that means choice E is also true, and so that is definitely not our answer either. The correct answer is C. Number 45 says let f be a function with second derivative given by f double prime at x equals sine of 2x minus cosine of 4x. How many points of inflection does the graph of f have on the interval 0 to 10? This is the first problem on the calculator portion where we really do want to be using a calculator. So I'm going to pull my calculator up here. You might have access to a different type of calculator, so just make sure you're familiar with how to use it on the day of the test. Now, just to clarify on how we find points of inflection of a function, what we're looking for is a sign change on f double prime. So this question is actually pretty easy. All we need to do is to input this function into our graphing calculator and just count how many times does the graph cross over the x-axis between 0 and 10. So let me take a moment and type in this function. If you're using something like a TI-84, you're going to put this into y equals. It's okay that the function is f double prime. You can just type it as f of x. We're just trying to take a look at the graph of that function. So let's type it in. Y equals sine of 2x minus cosine of 4x. And so here's our graph. We're going to want to zoom in a little bit. And really, this is kind of a lot to look at. So your calculator might be a little different, but on this particular graphing calculator, I can change the domain here. So I'm only looking at what I want to look at by typing in 0 is less than or equal to x is less than or equal to 10. It just makes the whole graph a little bit easier to digest to make sure that we're only looking in the correct domain. So here's the whole equation completely written out like that. This is the graph. I'm going to zoom in a bit because what we're looking for are how many times this thing changes sign. So you can see that down here our second derivative, which is what this is, even though we're calling it y, or maybe you're calling it f of x, but really this is the second derivative of f of x. We can see that it's negative until we hit this little x-intercept, and then it's positive, and then it's negative, 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 and then positive, and so on and so forth. So all we need to do is just count how many times the graph crosses over the x-axis, because those are going to be places where the value of our f double prime function is changing sign, and that's where our points of inflection are. So we can see that it's changing sign here once, twice. We're not going to count this x-intercept because it doesn't actually cross over, so the sign doesn't change. So once, twice, 3 times, 4 times, 5, 6, and finally 7. So that's it for this one. The graph of f double prime changes sign a total of 7 times between 0 and 10, so our answer is B. Number 46 says let g be a continuous function such that the integral from 0 to 2 of g of x dx is 7, the integral from 0 to 3 of g of x dx is 5, and the integral from 1 to 3 of gx dx is negative 1. What is the value of the integral from 1 to 2 of gx dx? When we find definite integrals, we can interpret the value of these definite integrals as being area bounded by the curve, g of x here, and the x-axis. And not just any old area, it is signed area, so that any area above the x-axis would be considered positive, and any area below the x-axis would be considered negative. Now here we don't actually know what the function is, we just know the value of some of these definite integrals. And so the way that I like to approach a problem like this is to just draw a number line to keep track of what area values we have so far and see if we can't just sort of logically work our way to get the area between 1 and 2. So here's my number line. Here's 0, 1, 2, and 3. These are really the only relevant numbers to this problem. So it says the area underneath the curve between 0 and 2 is 7. So that might go below the curve, and maybe there's a little bit more area above than below, but the net total area there is 7. So what I'm going to do is switch colors over here so that we can just mark and say, hey, from 0 to 2, that area is 7. Then it says that the area between 0 and 3 is 5. Say, okay, well, from 0 to 3 has an area of 5, which means that the area between 2 and 3 must be negative. Take a look at this. If the area from 0 to 2 is 7, but the area from 0 to 3 is 5, the difference has to be negative 2, because 7 minus 2 is 5. Finally, it says the area bounded by the curve g of x and the x-axis between 1 and 3 is negative 1. So between 1 and 3 is negative 1. And what we're interested in here is the area between 1 and 2. So from here to here, what is that? So let's go back and look and see what we have here. So if the area bounded between 2 and 3 is negative 2, that means like from here to here is going to be negative 2. And if the area bounded by the curve g of x and the x-axis between 1 and 3 is negative 1, then that is going to be all we need to know to be able to find this missing value, because these two numbers have got to add up to negative 1. So the integral from 1 to 2 gx dx plus negative 2, or in other words, minus 2, has to equal negative 1. So if I were to add 2 to both sides here, I'd get the integral from 1 to 2 of gx dx must be 1. So the value of this integral from 1 to 2 is 1. Number 47 says, let f be a differentiable function with domain from 0 to infinity and range all real numbers such that f of 2 is 3 and f prime of 2 is 1. The function f is increasing and the graph of f is concave down for all x in the domain. Let g be the function defined by g of x equals the inverse of f of x. So g is the inverse of f. On which of the following intervals is the derivative of g less than 1? I think the best way to approach this is going to be to sketch out a graph and do a little analysis on what's going on with the slope of g. So first, let's sketch out what f probably looks like. First, I'll start with the axes, and then we know 2, 3 is a point on the curve, so I'm going to go ahead and plot that. The domain is only positive values, and the range is all real numbers. It's increasing and concave down. So the curve is going to have to do something like this. It can't cross that y-axis, but it is going to be increasing and concave down. So it's going to be doing something like this. We also know that the slope of f at 2 is 1. So I'm just going to draw maybe a little line segment here, something like you would see on a slope field, where this slope right here is 1. So in other words, it's going like up 1 over 1. Now, g is the inverse of f. If 2, 3 is a point on f, then that means 3, 2 must be a point on g. On top of that, inverses are reflections of each other over the line y equals x. So if I just draw a little dotted line going down this way, I can get a pretty good idea of what that g function should look like. It's going to have to do something like this. So yeah, it's got that point 3, 2, and let's think about what the slope of g of x at this point must be. The slope of the inverse of f. So we have the inverse of f, and we want to find the derivative of that. We need to find 1 over f prime of f inverse x. F inverse is g, so I'm going to make this replacement and just call this g prime. And same thing over here. We'll just call this f prime at g. So if we're interested in the derivative of g at x equals 3, we can substitute that in. G of 3 is 2 because we have this point here. And let me move that over a little bit. So g prime at 3 is going to be equal to 1 over f prime at 2, and it gave us f prime at 2, which is 1. So this is 1 over 1, which verifies the slope of g at x equals 3 is also 1. Now, if f is concave down, which it is in this case, and increasing, that means that g is going to be concave up. So if the slope at 3 is 1, and it's concave up, that means the slope should be increasing. Every slope to the right of 3 is going to be bigger than 1. You can see this slope getting more and more steep. Similarly, if we go to the left of 3, these slopes become more and more horizontal, and they're getting smaller and smaller. The question here is, on which of the following intervals is g prime less than 1? In other words, where is the slope smaller than 1? Well, if the slope is 1 right here at x equals 3 and less than 1 to the left of it, that means the interval where g prime is less than 1 is from negative infinity to 3, so our answer is D. Number 48 says, starting at t equals 0, a particle moves along the x-axis, so its position at time t is given by the function x of t equals t to the fourth minus 5t squared plus 2t. What are all values of t
for which the particle is moving to the left. In order for a particle to be moving towards the left, the velocity must be negative. In other words, the velocity function is less than 0. Now, the relationship between position and velocity is that velocity is the derivative of position. So let's go ahead and find that velocity function. If x of t is t to the fourth minus 5t squared plus 2t, then the derivative of the position function using our power rule would be 4t cubed minus 10t plus 2. And since the derivative of position is velocity, that is going to be our velocity function. So what we're really interested in here is, when is this expression less than 0? And this is where the calculator is going to come in. Let's go ahead and pull it up. So yes, let's go ahead and type that in. V of t is equal to 4t cubed minus 10t plus 2. And we're looking for where that velocity function is negative. You can see it does start off negative here, but on the problem it says that we want to start at t equals 0. So we're not going to pay any attention to any of these negative t values. We'll go over here to where t starts at 0 and just look after that. And we can see there are two x-intercepts here, one at around 0.203, and this one is around 1.4. I suppose that would round to 70. And so this whole piece of the graph here, underneath the t-axis, will be where velocity is negative, and the particle will be moving to the left when the velocity is negative. So yeah, we're going to go from this t value to this t value. So our answer is B. Number 49 says the function f has a relative maximum value of 3 at x equals 1. So really quick, that means we have a point here, which is the maximum, 1, 3. And since it is a maximum, we know that the slope right here is 0. If h of x is another function that equals x squared times f of x, then what's the value of the derivative of h at x equals 1? So I'm going to rewrite this function h of x equals x squared times f of x. And if I want the value of the derivative of h, then I ought to find the derivative of h. So since h is a product of two functions, I'm going to use the product rule, which will give me the derivative of x squared, which is 2x, times f of x, plus the first function, x squared, times the derivative of the second. That's our equation for h prime, and the question is asking for h prime at 1. Let's substitute in 1 into each instance of x. And now we can simplify each of these little expressions here. 2 times 1 is 2. F of 1 is given as 3, so this will be 2 times 3, plus 1 squared, which is 1, and f prime at 1, which is the slope of f at x equals 1, which we already said was 0. So we get 2 times 3, which is 6, plus 0, so h prime of 1 is 6. The answer here is E. Number 50 wants us to find the indefinite integral of cosine squared x times sine of x. To evaluate this integral, we're going to use what is known as the anti-chain rule, but it's really more often called a u-substitution. If we let u be cosine x, then we can rewrite this integral as the integral of u squared, and then we have sine x dx. But if u is cosine x, then that means that the derivative of u would be the derivative of cosine, which is negative sine x dx. We do want to make a clean substitution here
And in our integral, we only have sine x dx, not negative sine x dx. So what we can do is actually just divide both sides by -1 here and get negative du equals sine x dx. That'll allow us to do a cleaner substitution. So since sine x dx is negative du, I can actually factor out that -1 and put it out here. And then we have du. Now we have an expression that is much friendlier to anti-differentiate. We can just use our anti-power rule and increase that power by 1 and divide by the new exponent. So we have -1/3 u cubed plus c, of course. Every time you find an indefinite integral, you're going to need that constant of integration. And now we've done it. We've already done the integration, so now all we need to do is just go back and substitute cosine x back into u. I'll rewrite this as -1/3 cosine cubed x plus c, which doesn't look exactly like any of the answer choices, but if we combine the -1/3 and the cosine cubed x, we can rewrite it as negative cosine cubed x over 3 plus c, and we can clearly see that the answer is A. Number 51 says the first derivative of the function f is given above. If f of 0 equals 0, at what value of x does the function f attain its minimum value on the closed interval 0 to 10? So a couple things to note here. First, f is going to be the integral of f prime. So it'll be the integral of square root of x sine x dx. And this is not something we're going to be able to find by hand or really even with a calculator as far as trying to find a closed form expression to represent this. So unfortunately, it's not going to be as easy as simply finding this equation, putting it into a calculator, and finding the minimum value. So we're going to have to think a little bit differently about this. The other thing I want to throw out there is that anytime we're looking for a minimum or even a maximum value, usually you want to use something called the candidates test, which is a way to find global or absolute maximum and minimum values on a closed interval. So if you have a closed interval like from 0 to 10, you would check both the endpoints, which would be 0 and 10, and any critical values of f. Critical values of f are going to be any x value that makes the first derivative either equal 0 or undefined, and this is where local extrema live. Any sort of absolute or global minimum or maximum is going to occur either at one of these local extreme values or at the endpoints. And so that's why we're going to use both endpoints and those critical values as potential locations for minimum and maximum values. So basically all you need to do is construct a little table here with both the endpoints, in this case 0 to 10, and all the critical values that fall in between. So let's find out what those critical values would be if we were to set f prime equal to 0. In other words, what are the solutions to f prime equals 0, where f prime is root x sine x? Now this expression is already factored to where we could use the zero product property and set each one of these equal to 0 and solve both of these to find all of our critical values. Either x is going to be 0 or sine of x is 0 anytime x is going to be a multiple of pi. So like pi or 0, 2 pi, all these, 3 pi, 4 pi, 5 pi, all these would be acceptable critical values. Although since we're just looking to be between 0 and 10, we're only going to pick out 0 pi, which is about 3.14, 2 pi, which is about 6.28, and 3 pi, which is going to be about 9.42. We've already got 0 in our candidates test table here, so the only ones we really need to include are pi, 2 pi, and 3 pi. So if we evaluate f of x with all these different inputs, whatever the smallest value is on this list will be the minimum value. And so we're looking not necessarily for the minimum value itself, but rather the x value where that minimum is. Evaluating f of x is going to be kind of tricky. We know that f of 0 is 0 because that was given, But other than that, we don't really know exactly what the rest of these are going to be because we can't really find the antiderivative of this expression. So this is where the calculator is going to come in, and we're just going to look at the graph and see if we can't answer this question just by understanding how integrals are calculated. So let me go ahead and pull up the calculator here, and I'm going to type in our derivative function here. So I'm going to, since I can't type it in as f prime, I'm just going to type it in as y. But we have the square root of x times sine x. Now, this is a graph from 0 to 10, and maybe I'll go ahead and put that domain restriction in here just so that all we're looking at are the x values between 0 and 10. And just keep in mind that this equation here is the derivative. This is f prime. And what we are interested in is the integral of this, which we're not really going to be able to put in. So there's two ways we could approach this problem. The first, and what I think is probably the better way to answer this question, is to look at the areas bounded between this curve and the x-axis. The integral of this function can be found if we can find the area that is bounded underneath here. So for instance, if we can find the area between 0 and pi here, that'll give us f of pi. So we don't really need to calculate this exactly. If we're looking at this graph, it's pretty easy to see that from 0 to pi, we have less positive area than we do from pi to 2 pi, meaning that from 0 to pi, we're going to have a positive integral value. But if we go all the way to 2 pi, we're going to have more negative area than positive area. So when we get to 2 pi, we are definitely going to end up with a negative integral. So we've got a positive integral value for pi, because we've got nothing but positive area here. We've got negative area at 2 pi, because we've got more negative area down here than we do in here. And then if we go all the way to 3 pi, we can see we've got even more positive area. If we look at this region plus this region, you can see there's definitely more area between these two regions than there is down here. So we're going to end up with another positive value. So at pi, we should have a positive number. At 2 pi, we should have a negative number. And then at 3 pi, we should have another positive number. At 10, it doesn't really look like there's enough negative area here to offset what we gained in this third region. We're just kind of playing this by eye and just kind of doing the eye test here, but it looks like the area underneath this curve and this curve over here, these two areas, if we add that up, should be greater than the area down here plus the area over here. And if you're not totally convinced by that, just kind of pair them up. What I mean by that is there's definitely more positive area here than there is negative area here. And there's definitely more positive area here than there is negative area over here. So at x equals 10, we should still have a positive value for f of x, which means that the minimum is going to have to occur at 2 pi, which is roughly 6.28. Our answer is D. Now, if you're not really convinced with this argument, as far as like looking at the areas, depending on your calculator, there may be a way for you to generate this table of values that we're working with here, just to verify that we got the right answer. So what we can do, at least in this calculator, is type it in like this. So I'm going to create a table here. And we've got x1 and we've got y1. I'm going to change this y1. And I'm going to change this to f of x. I'm going to type in all the values that we're using in our candidates test. So 0, pi, 2 pi, 3 pi, and 10. And then to calculate that integral, here's how you do it in this one. And again, depending on which calculator you're using, the steps for constructing this table might be a little different, but we want the integral from 0 to that x1, to this value, this x value, of f of x. You can see that the smallest value we have on this list is at 2 pi. So yes, this is going to verify what we found earlier. We don't really need those points there. That's not giving us anything extra. If you can find out how to construct this table in your calculator, you can also do the candidates test directly here without having to just sort of eyeballing these areas. But if you can eyeball the areas, you can definitely work this problem out a lot faster. So here we've got two ways of finding out that the correct answer is for sure D. Number 52 says the function f is differentiable with f of 1 equals 20 and f of 4 equals -4. Which of the following statements must be true? So we'll go through these one at a time and see if we can't come up with a counterexample or find a way to justify the fact that it must be true. Choice 1 says that the derivative of f, or the slope of f, is negative for all x in the open interval 1 to 4. Well, let's see if we can't sketch out a graph of what might be happening with this function. At x equals 1, the value of the function is 20. And at x equals 4, the value of the function is -4. I'm not trying to draw this to scale or anything, but just to give you a general idea of what might be happening with the function. Now, what this says is that the derivative, or the slope of f, is always negative. And we can definitely see that the slope is likely going to be negative, at least for some of the function, but it's not too hard to imagine a function that connects these 2 points in a way like something like this, where we can see there are multiple places on this graph where the slope is positive. So while it is possible that the entire slope is negative, it's not something that must be true. So 1 is not going to be one of the answers. Number 2 says there exists a number c where between 1 and 4 there's a value where f of c is 0. Since 0 is in between -4 and 20, meaning it's in between f of 4 and f of 1, we can use the intermediate value theorem as long as we can establish that this function is continuous on this interval. Now, the problem did say that f is differentiable along this interval, and since differentiability implies continuity, the intermediate value theorem will hold. And basically what the intermediate value theorem says is that as long as your function is continuous on the closed interval and differentiable on the open interval, that every single value between the initial and the final value must be accounted for. In other words, in order to get from 20 down to -4 down here, we're going to have to cross through that x-axis at some point. In other words, at some point, c, f of c, is 0. So 2 is going to be a correct statement, or a true statement. Number 3 says there exists a number c where between 1 and 4, the slope, or the instantaneous rate of change of f at c, is -8. To say whether or not this is true, we're going to reference the mean value theorem, which says that as long as f is differentiable on the open interval and continuous on the closed interval, which we've established so far, that there will be some point along this function, and again, we don't know exactly what the function's doing here. It could do something like that. It could even be a little simpler like that. Maybe it's concave down, who knows? But basically what the mean value theorem states is that at some point c, the slope of this curve, or the instantaneous rate of change of this curve, will be equal to the average rate of change. The average rate of change can be calculated by finding the slope of the secant line that passes through the 2 endpoints. So let's check that. The average rate of change will be the slope between these 2 endpoints. So in other words, f of 4 minus f of 1 over 4 minus 1. It's really just our classic slope formula of rise over run, or change in y over change in x. And f of 4 is -4. F of 1 is 20. So we get -4 minus 20, which would be -24 over 3, and that equals -8. So since the average rate of change equals -8, that means there must be some value between 1 and 4, we'll call c,
where the instantaneous rate of change is equal to that average rate of change. So 3 is another true statement, meaning our answer is D.
Number 53 says, let g be the function with first derivative given above and g of 1 equals 5. If f is the function defined by f of x equals the natural log of g of x, what is the value of f prime at 1, or the derivative of f at 1, or the instantaneous rate of change of f at 1? So let's go ahead and rewrite this function f of x, which is the natural log of g of x. To find the derivative of f, we are going to have to use the chain rule, which means we need to find the derivative of the outside function first. So the derivative of natural log of x is 1 over x. So this is going to be 1 over, instead of x, we'll put what was inside the function to begin with. But then the chain rule says that we have to also multiply by whatever the derivative of the inside function here is. So in this case, it's g prime. Now that we have an equation for f prime, we can find f prime at 1 by simply substituting in 1 for all the instances of x, 1 over g of 1 times g prime at 1. G of 1 was given in the problem. It said it was 5. So really the only thing we're going to need to evaluate here is g prime at 1. So let's go ahead and move forward with this. F prime at 1 is going to be 1 over 5 times g prime evaluated at 1. Now g prime is this function up here. So I'm just going to replace that one instance of x with a 1. So I have the tangent of 2 over 1 plus 1 squared. 1 squared is 1. 1 plus 1 is 2. 2 divided by 2 is 1. So f prime at 1 will be 1/5 times tangent of 1. Now up to this point, we really didn't need a calculator, but we're going to need one to evaluate tangent of 1. So let me break out the calculator over here. 1/5 times the tangent of 1. And so we get 0.311, which is answer choice A. Number 54 says, let r of t be a differentiable function that is positive and increasing. The rate of increase of r cubed, so that would be d dt, or the derivative of r cubed, this is going to give us the rate of increase of r cubed, is equal to 12 times the rate of increase of r. So that would be the derivative of r also with respect to t. When r of t equals what? So here we're trying to solve for r. We can go ahead and evaluate that derivative on the left-hand side using the power rule and a little bit of chain rule, since we're differentiating with respect to t, which is not the variable inside this expression. So we just want to be a little careful there. Using the power rule, we'll get 3r squared, but with the chain rule, we need to multiply by the derivative of r, which would be dr dt. From here, we can divide both sides by dr dt and get 3r squared equals 12. Divide both sides by 3 to get r squared equals 4, and then to get plus or minus 2. Now, since r of t is positive, we can disregard the negative solution here. So the answer is r equals 2, which is choice B. Number 55 says the function f is shown in the figure above. At which of the following points could the derivative of f be equal to the average rate of change of f over the closed interval -2 to 4? So this question is really just testing to make sure you understand the mean value theorem. And basically what the mean value theorem says is, as long as the function is continuous on this closed interval from -2 to 4, which it is, and differentiable along the open interval, which it also is, then at some point on the graph,
the slope, or the instantaneous rate of change, is going to equal the average rate of change. And the way that we find the average rate of change is to find the slope, or the rate of change, between the endpoints of the interval. So the slope of the line that I've just drawn here, which connects the two endpoints of the curve, is the average rate of change. And the mean value theorem says that whatever that slope is should be equal to the slope at some point on the graph of the instantaneous rate of change. So let's take a look at our choices here and just roughly sketch out what the tangent lines would look like with an eye on the slopes. And we're looking for the one that looks like the slope is the same as the slope of the secant line that I just drew. So at E, we can see that the slope is either 0 or pretty close to it. It definitely doesn't look parallel to that secant line, so it's not going to be E. D has a negative slope. The line tangent to the function at D is negative, so that's definitely not right. C is kind of like E, where it's either 0 or it's at least pretty close to 0. B looks like it could be a good candidate. Look at this line here. I'm just sketching, but it looks like it may be parallel to that secant line. A has a positive slope, but it is definitely not parallel. That slope is going to be much steeper than the slope of the secant line, which is the average rate of change. So the only reasonable answer here is B. Number 56 simply wants us to find the derivative of the integral of e to the t dt from 0 to x squared. There are really two ways we could approach this, both of which involve the fundamental theorem of calculus. There are two parts of the fundamental theorem of calculus, and you can solve this question by using either one. So I'm going to show you both so that you can pick and choose which way you like better. So I'm actually going to start with part 2 of the fundamental theorem of calculus. Part 2 gives you a way to evaluate a definite integral. So let me find that integral first. The integral from 0 to x squared of e to the t dt would be the net change of the antiderivative of e to the t. The antiderivative of e to the t is just e to the t. So if we evaluate that at t equals 0 and at t equals x squared and then find the difference, we'll find the value of that definite integral. So substituting in x squared is going to give me e to the x squared. Substituting 0 is going to give me e to the 0. And since e to the 0 is 1, so that's the value of the integral. But this question is actually asking for the derivative of that integral. So if we want the derivative of that expression, I'm going to actually go all the way back here and include that from the beginning. And now let's differentiate each term here. We will have to use the chain rule to find the derivative of e to the x squared. The derivative of e to anything is just e to that thing. And then using the chain rule, we need to multiply by the derivative of that thing. So the derivative of x squared is 2x. The derivative of -1 is just 0. So we can see here that our answer should be C. But let's check that with part 1 of the fundamental theorem of calculus. Part 1 gives us a way to sort of shortcut this process when the limits are variable. So I'm going to start back over from the beginning. The derivative of the integral from 0 to x squared of e to the t dt. Part 1 of the fundamental theorem of calculus says that if we want to find the derivative of that integrable function, we can simply take that upper limit and substitute it for every instance of t. So this will equal e to the x squared, and then because of the chain rule, we need to multiply this by 2x. So we end up with the same answer that we got when we used part 2. Whether you use part 1 or part 2 here, we can see that the answer is C. Number 57 says, a college is planning to construct a new parking lot. The parking lot must be rectangular and enclose 6,000 square meters of land. A fence will surround the parking lot, and another fence parallel to one of the sides will divide the parking lot into 2 sections. What are the dimensions in meters of the rectangular lot that will use the least amount of fencing? As soon as I see that phrase, least amount, that tells me that I'm going to be looking for a minimum.
Now, before we work this out, let's go ahead and sketch out what's going on here. We've got a rectangular parking lot, and I'll call these two dimensions x and y, and then another line of fencing that is parallel to one of the sides that divides the parking lot into two equal sections. So I'm going to just draw that going along here. Okay, going back to the problem, it's asking for the dimensions that will require the least amount of fencing. And so we're looking for a minimum on this fencing function that will produce the number of meters of fencing that we need to complete this project. So let's start by writing out what that function would be. So the amount of fencing required is going to be 3 of these x's, like 1, 2, 3, plus 2 y's. We have two sides over here that are both y. Because this is a function in terms of x, we're going to want to rewrite that y variable in terms of x so that finding the minimum is a little bit easier. There's one other equation that we're going to need to consider here, and that's the fact that we have an area of 6,000 square meters. So the way that we find area of a rectangle is length times width or base times height. Basically, you just multiply the two dimensions together. And so in this case, the two dimensions would be x and y. So the area would be x times y. If the area is 6,000 square meters, then we can rearrange this and come up with an equation for y in terms of x. Y would be 6,000 divided by x. So this expression can be used instead of y in our fencing function. So I'm going to replace this y, and this might be worth just writing as a separate line here, with 6,000 over x. This function will give us the amount of fencing that's required, and if we want to find the minimum amount of fencing, we're going to need to first find a critical value of this function and decide whether or not it's a maximum or a minimum. So the way we find critical values is by setting the derivative equal to 0 and solving. One last thing that might make finding this derivative a little easier is to rewrite that last term as 2 times 6,000, which is 12,000. And instead of writing this as divide by x, you can write it as times x to the negative 1. So now we're ready to write our derivative function. The slope of 3x is just 3, and then using the power rule, negative 1 times 12,000 is actually going to make this minus 12,000, and then x to the negative second power. Now we can find our critical values by setting this function equal to 0 and solving for x. Subtract 3 from both sides, and then divide both sides by negative 12,000. Since we're trying to solve for x here, it might be nice to have a positive exponent. So what we could do is raise both sides to the power of negative 1, which effectively reciprocates both sides of the equation here. So instead of 3 over 12,000, I'm going to have 12,000 over 3, which actually reduces 12,000 over 3 is going to be 4,000. So if I reciprocate both sides of this equation, I'm going to get 4,000 equals x squared. And I'm kind of running out of room here, so I'm going to continue up here. Taking the square root of both sides is going to give me x equals plus or minus the square root of 4,000. Because of the context of this problem, though, we're going to ignore the negative solution here and just stick with the positive solution. So we have x equals the square root of 4,000. This can be simplified. If I divide out a 400 out of that 4,000 and rewrite this as 400 times 10, I can then go and just take the square root of 400, which is 20, and rewrite this as 20 times root 10. So now we just found the x dimension, and normally we'd have to go back and find the y dimension too, but there's only one answer choice that has 20 root 10 as one of the possible dimensions. So I'm pretty sure that our answer is going to be C here, but I think it'd be worth just checking real quick to make sure that the y value is correct too. So going back to one of the original equations that we wrote, that the area is x times y here, when we know the area is 6,000, we can fill that in along with our value for x to solve for y. And now I'm really running out of space here, so I'm going to try to squeeze this in up over here. The area is 6,000. The x is 20 root 10, and we're going to use that to solve for y. So if I divide both sides by 20, we'll start with that. That's going to give me 300 equals root 10y. And then dividing both sides by root 10 is going to give me 300 divided by root 10. If I simplify that by multiplying both the top and the bottom by root 10, I'm going to get 300 root 10 over 10. And I'm really struggling to find a space to write this. Maybe I'll write it down here. 300 divided by 10 is 30. So y is 30 root 10. So that does check out here, and we can verify that our answer is in fact C. Number 58 says the function f is continuous on the closed interval from 0 to 6 and has values shown in the table above. Let L represent the left Riemann sum approximation of the integral of f of x dx from 0 to 6 with 3 subintervals of equal length, and let R represent the right Riemann sum approximation of the same integral with the same subintervals of equal length. What is the absolute value of L minus R? So just to make sure we understand what a Riemann sum is, let's say that we were to plot the points given in the table. I've sketched it twice here so that we can see the difference between a left Riemann sum and a right Riemann sum. The question does say f is continuous, so while we don't know exactly what the function is doing, we do know that these points are connected in some way. So it might be doing something like that, or maybe something like this, who knows? That part is really not important. What is important is that we understand what a Riemann sum is used for and how we compute it. So typically in calculus, when we are trying to find the integral from, say, 0 to 6 of f of x dx, what we're looking for is the area bounded by the curve and the x-axis, or if we're going to use the fundamental theorem of calculus to calculate it, we would find the net change in the antiderivative of f of x. But the integral does still equal the area bounded by the curve and the x-axis. So if we don't know what that curve is, we can use a Riemann sum to approximate that value. Now, while there are a few different ways of coming up with this approximation, a Riemann sum is one where you basically just draw rectangles that have heights based on the points that are given and find the area of each of these rectangles, add them up, and that'll give you your approximation. The difference between a left Riemann sum and a right Riemann sum has to do with which partition of these intervals are you going to use for the height. So, for example, the left Riemann sum is going to look at this first interval from 0 to 2, so with the right Riemann sum. But when we draw a rectangle up to where the curve is going to be, the left Riemann sum will use the left partition to determine the height, whereas the right Riemann sum will use the right partition to determine the height. So the first rectangle on a left Riemann sum for our approximation is going to look like this, whereas the first rectangle on the right Riemann sum is going to look like this. So for each of these intervals, for the left Riemann sum, it'll be the left partition that determines the height of each rectangle. And so you're going to find the areas of all three of these rectangles. For the right Riemann sum, you'll find the area of all three of these rectangles. To answer this question, we are looking for the absolute value of the left Riemann sum minus the right Riemann sum. So we're going to need to find the value of each one of those. The left Riemann sum is going to be the sum of the areas of all of these rectangles, whereas the right Riemann sum will be the sum of the areas of these three rectangles. So for the left Riemann sum, we can find the area of the first rectangle by multiplying 2 times 9. 2 would be the interval length here, and that is actually going to be consistent with all of these interval lengths. And then since it's a left Riemann sum, we'll use the left partitions for the height. So the left Riemann sum will equal 2 times 9 plus 2 times 5 plus 2 times 3, whereas the right Riemann sum will be 2 times 5 plus 2 times 3 plus 2 times 1. So the left Riemann sum is 18 plus 10 plus 6, and the right Riemann sum is 10 plus 6 plus 2. The left Riemann sum would be 28 plus 6, which is 34, and the right Riemann sum would be 10 plus 6 is 16, plus 2 is 18. So if we want the absolute value of L minus R, that's going to be the absolute value of 34 minus 18. And 34 minus 18 is 16. The absolute value of 16 is also 16, so the answer is D. Number 59 says, the graph of the continuous function f consists of 3 line segments and a semicircle centered at point 5, 1, as shown above. If capital F of x is an antiderivative of lowercase f of x, such that capital F of 0 is 2, what is the value of capital F of 9? So this really boils down to understanding the fundamental theorem of calculus. Part 2 of the fundamental theorem of calculus says that if capital F is an antiderivative of little f, then the integral from a to b of f of x dx is equal to the antiderivative value capital F at b minus capital F, which is the antiderivative evaluated at a. In other words, the integral from a to b of any function is equal to the net change in the antiderivative of the function you're integrating. In this problem, we're interested in the values of f0 and f9. So I'm going to use those values for the limits of my integral and rewrite this as the integral from 0 to 9 of f of x dx equals capital F of 9 minus capital F of 0. For this problem, we're trying to find the value of f of 9. And so I'm going to rearrange this equation to say that capital F of 9 equals the integral from 0 to 9 of f of x dx plus capital F at 0, which was given in the problem. So we can actually replace this capital F of 0 with 2. I'll do that on the next step. Really what this problem is going to hinge on is going to be your ability to calculate this integral here. So while you can use the fundamental theorem of calculus to find the value of a definite integral, another way you can find the value of a definite integral is to find the area bounded by the curve and the x-axis. And not just the area, but what we'll call signed area, where we treat all the area above the x-axis as positive and all the area below the x-axis as negative. So in other words, to evaluate that integral, we're going to need to find all of this area plus all of this area, and then subtract this negative area down here. Since this piecewise function consists of nothing but line segments and little circular component in the middle there, we should be able to use some basic geometry formulas to find this area. The easiest way to do that is going to be to split this up into little portions like this so we can find each little area separately. So let's start with the sort of the easiest one here, which is the rectangle. The area of this rectangle right here is going to be 2 by 1, so the area here is 2. And I'm just going to make a little note here, 2 times 1 is 2. Now I'm going to look at some of these triangles that we've got going on here. For this one over on the left, we can see that it's a 2 by 1 triangle. The formula for a triangle is half base times height. So half times 2 times 1 is just 1. Next, I'll look at the other two triangles, which should have the same area, although one's positive and one's negative. If you recognize that, then you can see that these two areas are just going to cancel each other out. You can compute them separately by doing 1.5 times 1 divided by 2, 1.5 times 1 divided by 2. But since the area above the x-axis is considered positive and the area below the x-axis is considered negative, the value of these two areas are just going to cancel each other out and add up to 0. So we can safely ignore both of those. So the last piece to get is this area underneath that circular curve, all of this area. And probably the easiest way to find this is to find the area of this rectangle here and then subtract the area of this semicircle. So basically we have the area of the rectangle, and if we take away all of this that I'm trying to highlight here, this area of this semicircle, we should be left with the area underneath. So we have the area of the rectangle minus the area of the semicircle. The area of the rectangle, since it's a 2 by 1 rectangle, is 2. And then the formula for area of a circle is pi r squared.
this is only half of a circle, so it's half pi r squared, with the radius being 1. So it's 1/2 times pi times 1 squared. So that would just equal 1 squared is 1 times 1/2 is 1/2 pi. The area of this little purple region here, let me just kind of erase the rest of this since we don't really need it anymore. The area of this purple region here is going to be 2 minus half pi. So let's go back and fill in everything that we know now back into this fundamental theorem of calculus equation. F of 9 is what we're trying to find. The integral from 0 to 9 is going to be 1, which is that triangle, plus 2, which is the green rectangle, plus that purple area, which is 2 minus 1/2 pi. Normally we'd have to find the rest of the area, but those two triangles' areas are going to offset each other, so that's it for that. This right here is the value of this integral. The value of f of 0 is 2, and that's given right here in the problem. So we have an extra plus 2 here, and we're almost at our answer here. We just need to combine all of our like terms. So we've got 1 plus 2 is 3, plus 2 is 5, plus another 2 is 7. So this is going to equal 7 minus pi over 2. Our answer is D. Number 60 says a spherical balloon is being inflated at a constant rate of 25 cubic centimeters per second. At what rate in centimeters per second is the radius of the balloon changing when the radius is 2 centimeters? The volume of a sphere with a radius r is 4/3 pi r cubed. This is going to be what's known as a related rates problem. And for these problems, what you need to do is differentiate both sides of your equation with respect to t. So the derivative of volume with respect to t is going to be dv dt. The derivative of the right-hand side with respect to t is going to work just like how you would differentiate normally, except you have to use the chain rule when differentiating the variable. So the derivative of 4/3 pi r cubed would be using the power rule for pi r squared, and then because of the chain rule we need to differentiate the r with respect to t, so we get dr dt. Next we can fill in all the known information. The rate at which the volume is changing is 25 cubic centimeters per second, so this is our dv dt. I'll replace that with 25. The radius is 2 centimeters, so I'm going to replace r with 2. And then the dr dt is the rate at which the radius of the balloon is changing. So that is actually what we're trying to solve for. So we need to simplify this equation a little bit and then rearrange so that we can isolate the dr dt. 2 squared is 4, and 4 times 4 is 16. So we get 16 pi times dr dt. And then we could divide both sides by 16 pi to get 25 over 16 pi. That's our dr dt, which again is the rate at which the radius of the balloon is changing. The units here, they don't ask for them, but this is in centimeters per second. Our answer is A. Number 61 says R is the region below the curve y equals x and above the x-axis from x equals 0 to x equals b, where b is a positive constant. Before we go any further, let's sketch out what region R actually looks like. Here are my x and y axes. The equation y equals x is going to look something like this. And we're interested in the area below that curve, to the right of x equals 0 and to the left of x equals b. So if we put b somewhere in here, we're looking for this area. R is this area in here. S is the region below the curve y equals cosine x, above the x-axis between x equals 0 and x equals b. We want to sketch a curve of cosine x. So if you don't know what cosine of x looks like, that's okay. You can always type it in. Basically, it's going to do something like this. And let's say b is right here. In that case, region S would be this region in here. What the question is actually asking us here is, for what value of b is the area of R equal to the area of S? So the way we find the area bounded between the curve and the x-axis will be with a definite integral. Area R is going to be the integral from 0 to b of y equals x dx. And the area S will be the integral from 0 to b of cosine x dx. So what we're trying to find is what value of b makes both of these areas the same. So we want to set both these integrals equal to each other in an effort to find b. The antiderivative of x is 1/2 x squared, and we'll evaluate that from 0 to b. The antiderivative of cosine x is sine x. We'll be evaluating that from 0 to b. Now we can substitute in b and substitute in 0 to both of these equations, find the difference, and hopefully we can solve for b without too much trouble. Substituting in b here is going to give me 1/2 b squared. And then if I substitute 0, I get 1/2 0 squared, which is just going to be 0, but I'll leave that there for now. Sine of b on the right-hand side minus sine of 0. So let's clean this equation up just a bit. On the left-hand side, we have 1/2 b squared minus 0, so I'm just going to leave it as 1/2 b squared. And on the right-hand side, since sine of 0 is 0, we just have sine of b. So this is an equation that is not really going to be able to be solved by hand. We're going to have to use the calculator. So let me pull out the calculator. And to solve this, the easiest way is to set up a system of equations and then find the point of intersection. So the first one, 1/2 b squared, I'm actually going to type it as 1/2 x squared. And instead of typing in sine b, I'm going to type in sine x. So we have both of those curves. And what we're looking for is the point of intersection. So basically the x value where both of these are the same. That will ensure that both of these are the same. So there's one at 0, but we're not really interested in that one. We're interested in this one over here, where the x value is, or in our case, the b value is 1.404. And so you can see that the answer is D. Number 62 says, let f be a function defined by f of x equals e to the power 3x, and let g be the function defined by g of x equals x cubed. At what value of x do the graphs of f and g have parallel tangent lines? So by parallel tangent lines, what we're really looking for here is where are the slopes the same? The derivative of a function describes that function's slope for any x value. So really what we need to do here is find the derivatives of both f and g, set them equal to each other, and then solve for x. So let's start with just the derivatives, f prime and g prime. When are they equal? For what x values are the slopes of those two functions the same? The derivative of f is going to be e to the 3x, and then because of the chain rule, we need to multiply by the derivative of 3x, which is 3. The derivative of g, using the power rule, will be 3x squared. So what we have here is 3e to the 3x equals 3x squared. This is an equation that can be solved using the calculator. You really don't want to try to solve this any other way. So let me go ahead and pull up that calculator. Solving an equation with a graphing calculator is pretty simple. All you need to do is put in both sides of the equation as two different functions. So the left-hand side here, 3e to the 3x, is what we'll type into the first equation, and the second equation should be the right-hand side, 3x squared. And what we're looking for is where these functions intersect, and we can see a point of intersection right here, and that will round to approximately negative 0.484, so our answer is C. Number 63 is about as direct of a question as we can expect to get. It's simply asking for the derivative of the inverse sine of 5x. So there's two things at play here. One is you got to know your inverse trig function derivatives. So if you don't already know these, make sure that you study at the very least the derivative of the inverse sine of x. which is 1 over square root of 1 minus x squared. While we're at it, although you don't need it for this problem, the derivative of the inverse of cosine is negative 1 over the square root of 1 minus x squared, and the derivative of the inverse of tangent is 1 over 1 plus x squared. If you really got a lot of extra time, you could also learn the derivatives of arc secant, arc cosecant, and arc cotangent. But I find that knowing these particular three is not as helpful as knowing the main three: inverse sine, inverse cosine, and inverse tangent. If you know these three, you should be in pretty good shape. Now, the other thing that we're going to need to know to solve this problem is how to use the chain rule. Anytime you've got a composite function, which is where you have some function living inside another function, the way you find the derivative is first to apply the derivative of the outside function. So since the derivative of inverse sine is 1 over the square root of 1 minus x squared, the derivative of inverse sine of 5x is going to be 1 over the square root of 1 minus, and then instead of x, we'll have 5x squared. Now that's just the first part. Because of the chain rule, we also need to multiply that by the derivative of the inside function. So the inside function being 5x has a derivative of 5, so we need to multiply that by 5. And we're pretty much done here, except we need to simplify this expression just a little bit. So if I multiply that fraction by 5, I can rewrite that as 5 over the square root of 1 minus, and then 5x squared is the same thing as 5x times 5x, so that would be 25x squared. Our answer is D. Number 64 says the population P of bacteria in an experiment grows according to the equation dp dt equals kp, where k is a constant and t is measured in hours. If the population of bacteria doubles every 24 hours, what is the value of k? Whenever you have a rate of change that is proportional to a function, that function is going to be exponential. And the way that we can show that that is going to be true is by using a technique called separation of variables to anti-differentiate to solve for that function p. So let's go ahead and do that. We'll start with the dp dt, or the derivative of the population with respect to time, which equals kp. With the separation of variables technique, you want to identify the two different variables that you're working with, and those are going to be the ones that appear in the differential. So in this case, p and t. And you might be a little confused because there's no other t in this equation, but that's okay. Basically, what we want to do here is move all of the p variables to one side and all the t variables to the other side. So for instance, if I want to move the dt over to the right-hand side, I can multiply both sides by dt. And I also want to move that p over to the left side. So when I divide both sides by p, I'm going to get 1 over p, which is the same as p to the negative 1 dp equals k dt. Now that I've got a differential on both sides of this equation, I can go ahead and integrate both sides of this equation. So I'm going to integrate the left-hand side with respect to p and the right-hand side with respect to t. One of the antiderivatives that you just need to know is the antiderivatives of x to the negative 1, or 1 over x. If I try to integrate x to the negative 1, I'm going to get the natural log of the absolute value of x. And yeah, there's a plus c, but we don't really need to worry about that quite yet. So on the left-hand side, after I integrate p to the negative 1, or 1 over p dp, we're going to get the natural log of the absolute value of p. When I integrate the right-hand side, we're going to treat k as though it's a constant, and it even says it's a constant. But even if it wasn't, we'll treat it as a constant when we anti-differentiate with respect to t. The antiderivatives of this will be kt plus some constant. Now technically we did get a constant over here too, but I'm just going to subtract that constant from both sides and let this constant absorb both of those. Now I'm going to try to solve for p, and so the first thing I'm going to do is try to get rid of that natural log. Since the inverse of a natural log is e to the x, I can raise both sides as powers of Euler's number e to get something like this. E to the natural log of the absolute value of p equals e to the kt plus c. The whole reason I did that, like I said, because exponentials and logarithms are inverses. So the left-hand side is just going to simplify to the absolute value of p. And I'm actually going to rewrite this right-hand side just to make it a little easier to deal with. There is an exponent property that says when you multiply two powers with the same base, you can combine those by adding the exponents. And so what I'm going to do is use that property backwards and split up that right-hand side into e to the kt times e to the c. Now, since e is Euler's number is a constant, right here we just have a constant raised to the power of another constant. So that constant can just be absorbed into a new c. I'm going to rewrite this now as absolute value of p equals this new constant c times e to the kt. Within the context of this problem, it really doesn't make sense to have a negative population. So dropping the absolute value bars would normally require us to put a plus minus on the right-hand side. But since we can't really have a negative population, we're just going to ignore the negative part of it and just go ahead and drop those absolute value bars. Now that we've used the separation of variables technique to solve for the function p, we can now go ahead and start to answer this question. It says, if the population of the bacteria doubles every 24 hours, what is the value of k? If the population is doubled every 24 hours, then the new population is going to be twice whatever the initial amount is. And in an exponential function, the coefficient of the exponential term is the initial amount. So if our constant c here is the initial amount, then if that amount doubled, then the new population would be 2c. And the time that it took for that to double was 24 hours, so I'm going to substitute that in for t. Next, I can divide both sides by c, which is going to cancel these out, leaving me with 2 equals e to the power of 24k. Now I want to use the natural log function on both sides of this equation to get rid of that Euler's number. Kind of like the opposite of what we did from here to here. So when I take the natural log of both sides, I get the natural log of 2 equals 24k. And then I need to divide both sides by 24 to get k equals the natural log of 2 over 24. That's about as far as we can go without a calculator here. And we do want to calculate out that value and see which one of these decimals is equal to that. So I'm going to pull up my calculator. And all I need to type here is the natural log of 2 divided by 24. We can see that that's approximately 0.029. Our answer is A. Number 65 says the graph of the function f is shown in the figure above. What is the value of the limit as x approaches 3 of 4 minus 2f of x? So let's take a closer look at that limit. We can use our limit properties to split this up as the limit as x approaches 3 of 4 minus 2 times the limit as x approaches 3 of f of x. Whenever you find the limit of a constant function where there's no x and all you have is a number there, that is going to be the value of the limit. So the limit as x approaches 3 of 4 is just 4. We have 4 minus 2 times the limit as x approaches 3 of f of x. And to evaluate that, we need to take a look at the graph. To find a limit, you're going to look for the value that the function is approaching, not necessarily what it equals. So we're not looking to find what is f of 3, but rather what is f approaching as x gets closer to 3. As you look at the graph from both the left-hand side and from the right-hand side, on both sides we're getting closer and closer to this point right here. Even though that's not the value of the function, we don't really care about that because we're not trying to find f of 3, we're trying to find the limit of f of x as x approaches 3. So the y value here is 2. So the limit of f of x as x approaches 3 is negative 2. So we have 4 minus 2 times negative 2. And we can simplify this to 4 plus 4, which is 8,
Our answer is E. Number 66 says, during a snowstorm, the rate in inches per hour at which snow falls on a certain town is modeled by the function r of t, where t is measured in hours and is between 0 and 4. Based on the model, what is the total amount of snow in inches that fell on the town from t equals 0 to t equals 4? So really what this is asking for is how much snow was accumulated during that time. Another way of thinking about this question is that it's looking for the net change in the antiderivative of r, since r is a rate in inches per hour, and we're looking for the number of inches of snow that fell. So to calculate this, all we really need to do is find the integral from 0 to 4 of that function r of t dt. And this is something that you'll use a calculator to evaluate. So let me go ahead and pull up my calculator, and I'll go ahead and type this in. The integral from 0 to 4 of r of t, which I'll go ahead and type it out explicitly here, negative cosine t minus 0.9 t plus 3. We will need parentheses around this expression, and of course we need the dt at the end. But once you type it in, it should give you the result, which is 5.55 rounds to 7. The answer choice that is the closest to this number is D, 5.6. Number 67 says the function f is defined by f of x equals the integral from 1 to x of sine of the square root of t dt for all values between 1 and 12. At what value of x does f attain its absolute maximum value, that's a y value, on the interval 1 to 12? Normally with these kind of problems, we want to be using the candidates test to find absolute extrema. And usually with the candidates test, what you want to do is first find all the critical values of the function that you're trying to find the absolute maximum for, then test all the critical values and the endpoints of the interval, which in this case would be 1 and 12, by plugging in the critical values and endpoints into x and checking to see what value is the largest or the smallest out of those potential candidates. That's why it's called the candidates test. But since we get a calculator on this problem actually becomes rather trivial. So let me take out the calculator and show you what I mean. We're not really going to have to show any work here. All you need to do is type in the function they gave you. So we have f of x equals the integral from 1 to x of sine of the square root of t dt. And once the graph comes up, try to find that maximum, which is going to be right here. And so we can see that it happens at roughly 9.870. So our answer is D. Number 68 says an object on the moon is launched upward with an initial velocity of 25 feet per second from an initial height of 40 feet above the ground. The acceleration of the object is negative 5.3 feet per second, or feet per second squared. How many seconds after the launch does the object hit the ground? This is not a multiple choice question, so we're just going to have to cross our fingers and hope that what we get is correct. This is not a multiple choice section, so we will have to fill in our answer manually. Let's analyze what the given information is. First, the initial height is 40 feet. So I'm going to make a little note here that the height at time 0 is 40 feet, and that's what the word initial is referring to. It also says the initial velocity is 25 feet per second. And finally, the acceleration is a constant negative 5.3 feet per second squared. The question is asking, how many seconds after the launch does the object hit the ground? Well, since the ground is going to have a height of 0, what it's really asking is, when is the height function equal 0? The relationship between the height, the velocity, and the acceleration is the same as the relationship between position, velocity, and acceleration. And that is that the velocity
will be the derivative of the height, and the acceleration will be the derivative of velocity. Since we have our acceleration function, we can anti-differentiate that to find the velocity function, and then again for the height function. So the velocity function can be found by integrating the acceleration function, which is just a constant negative 5.3. So when we integrate that with respect to t, we're going to get negative 5.3t plus some constant. The way that we're going to find the constant is by using this data point right here, the fact that the velocity at 0 is 25. So since the velocity at 0 is 25, we can set 25 equal to negative 5.3 times 0, since the time is 0, plus c, which tells us that the c value is actually 25. So our velocity function now is negative 5.3t plus 25. Now we can use that to get the height function in a very similar way. The height function is going to be the integral of the velocity function, again with respect to t. Using our anti-power rule, we're going to raise that exponent by 1 and then divide by the new exponent. So we're going to take this negative 5.3 and divide that by 2. I'd really recommend you use that calculator to do that, but you should get negative 2.65. Using the anti-power rule again, our next term will be plus 25t, and then we still have another constant on this. So we will have to find that last constant to really flesh out this height function, and we can use this point up here, the fact that the height is 40 feet when time is 0, to find that constant. So let's set that height equal to 40 and the time equal to 0 on that height function. And since both of these terms will just zero out, 40 is that c value. So our height function is negative 2.65 t squared plus 25t plus 40. Now the question here is, how many seconds after the launch does the object hit the ground? In other words, what is the time when height is 0? So let's set that height equal to 0 and solve for time. So we can use a calculator to do this. And let me go ahead and pull out that calculator. Just type in the height function. And we're looking for where the height hits the ground. We can see that's right here. If I change my scale a little bit, we can see the entire path of this object. And you can see, yeah, it does go ahead and start at 40 here. Goes up. We don't really care about the maximum, but you could find it. And then we also have the time at which it hits the ground. Now the problem does say, give your answer to the nearest integer. So we're going to round this to 11 seconds. Number 69, nice, says let f be a function with derivative defined by f prime, or the derivative of f equals x squared minus 4x all over x minus 2 squared, on which of the following intervals is the graph of f both decreasing and concave up. In order for f to be decreasing, the first derivative has to be negative. And in order for f to be concave up, the second derivative has to be positive. Now, this is a problem that is totally solvable without a calculator, but the calculator makes this so much easier. And because this question is on the calculator section, I say let's just go ahead and take advantage of that. So let me go ahead and pull up my calculator here, and let's type in that f prime function. Y equals x squared minus 4x all over x minus 2 squared. So as we try to find where the function f is decreasing concave up, let's just be aware that this function right here is the first derivative. So first, let's just make sure that the function f is decreasing, which only occurs when f prime is negative. And we can zoom out on this graph and see exactly what's happening here. It's only going to be negative, in other words, below the x-axis. It looks like between 0 and 4. So f is decreasing on this interval from 0 to 4. F is concave up when the second derivative is positive. Since we're looking at the graph of the first derivative, the second derivative will be positive wherever the first derivative is increasing or has a positive slope. And so we're only really looking here between 0 and 4. And so we want to find where is the slope of this f prime function positive. And we can see that it's going to be negative from 0 to wherever that asymptote is. And from that asymptote all the way to 4, the slope will be positive. So if we can identify where that vertical asymptote is, our answer here is going to be from there to 4. Really, the only answer choice that makes sense here is answer choice C, and that does look right. The asymptote for sure is at 2, and we can see that 2 makes this function undefined. So yeah, our answer is choice C. Number 70 is the last problem on the calculus exam guide, so let's get at it. Let f be a continuous function such that f of x is greater than or equal to 0, meaning it's not negative, on the interval from 0 to 2. F of x is less than or equal to 0 on the interval 2 to 5. The integral from 0 to 2 of f of x dx is 6, and the integral from 2 to 5 of f of x dx is negative 8. What is the value of the integral from 0 to 5 of f of x plus the absolute value of f of x dx? Using our properties of integrals, we can split this up as the integral from 0 to 5 of f of x dx plus the integral from 0 to 5 of the absolute value of f of x dx. Given that we've got an integral from 0 to 2 and 2 to 5 separately, it might be better to rewrite an integral from 0 to 5 of f of x dx as the integral from 0 to 2 f of x dx plus the integral of 2 to 5 f of x dx. So I'm actually going to do that with both of these integrals. So the first one would be exactly what I wrote above, and I'll do basically the same thing with that next integral. Once we have it all separated out like this, we can just use the values that were given. So the integral from 0 to 2 of f of x dx is 6. The integral from 2 to 5 of f of x dx is negative 8. The integral from 0 to 2 of the absolute value of f of x is also going to give us 6, because 6 is already positive, and when you take the absolute value of a positive number, it remains positive. Now, when we're trying to find the integral from 2 to 5 of the absolute value of f of x dx, since the absolute value changes any negative values to positive, instead of getting negative 8, we're going to get positive 8. So at this point, we just need to add up all of our numbers here. 8 minus 8 is 0, and 6 plus 6 is 12. Well, that about wraps up these 70 problems that are on the calculus exam guide. If you made it all the way to question 70, I've got to give you major props because this is a lot of questions. But overall, thanks for watching, and y'all have a great day.